This lesson deals with the direct reading or direct indicating magnetic compass and describes the principle of operation, the effects of acceleration and turning errors, and how to interpret the direct reading compass indications in a turn. A magnetic compass uses the horizontal component of the Earth's magnetic field to indicate the direction over the surface of the Earth of the magnetic poles, and the aircraft's heading is based on this magnetic datum. The direct reading magnetic compass enables the pilot to directly read the aircraft's heading from a pivoted magnetic compass assembly. The vertical card compass, or E-type compass as it is commonly known, is a type in general use. It is quite usual for the E-type compass to be the main magnetic reference source in a light aircraft and a standby compass in larger aircraft. The maximum permissible deviation on any heading is 10 degrees. The E-type compass consists of a circular compass card attached directly to the magnet assembly, which is suspended in liquid within a compass bowl. A vertical lubber line on a glass window in the compass casing enables the heading to be read off the compass card. Later in the lesson, we will try turning onto a heading using the E-type compass to see how it works in practice. In the meantime, we need to consider the three basic properties a direct reading compass must possess. They are horizontality, sensitivity, and a periodicity. Let's look at each one in turn. It is the horizontal or H component of the Earth's magnetic field which enables the compass magnets to positively align themselves with the Earth's magnetic field in a north-south direction. The Earth's magnetic field will only be horizontal, however, along the acclinic line, or magnetic equator. Even in mid-latitudes, lines of magnetic force in the Earth's magnetic field dip significantly below the horizontal. A freely suspended magnet assembly would follow the angle of dip, so to counteract this effect, the magnet assembly is pendulously suspended. A non-pendulously suspended magnet would take up the inclination of the local dip, like this. By suspending it from above, on a sharp pin sitting in a smooth, hard cup, we displace the centre of gravity from the centre. This produces a self-levelling mechanism. The centre of gravity will seek the lowest point. This means that the tilting effect caused by the vertical or Z component of the Earth's magnetic field is opposed by the weight of the magnet assembly, and the tilt or dip will be greatly reduced. Unfortunately, as we shall see later, this solution introduces new problems, called turning and acceleration errors, which we will discuss shortly. The sensitivity of a magnetic compass is its ability to accurately point to magnetic north. Two factors will affect this. The first is the strength of the Earth's magnetic field. The second factor is the pole strength of the compass needle or assembly. The weak magnetic field of the Earth cannot be altered. So to increase the sensitivity of the compass, multiple short magnets with a high degree of magnetism are incorporated into the magnet assembly. Sensitivity is further increased by reducing friction, and this is achieved in three ways. The first is to use an iridium-tipped pivot in a jeweled cup. The second is the lubricating effect on the pivot by the liquid which fills the compass bowl. And thirdly, the liquid in the compass bowl helps reduce the effective weight of the magnet assembly, as liquid is denser than air. A periodicity is a measure of how quickly the magnetic compass settles down to accurately point towards north again after being displaced. Any oscillations of the compass needle around magnetic north must be damped out or substantially reduced, and this is achieved in two ways. The first is the use again of multiple short magnets in the assembly. In this way, the mass of the magnet assembly is kept near the centre of the unit, which reduces the moment of inertia. The second way is the use of liquid in the compass bowl. This acts as a damping agent. However, when using liquid in this way, there are two other issues to consider. The first is that liquid may expand or contract as temperature changes, and this can be overcome by incorporating an expansion chamber. The second issue is that of liquid swirl, and this occurs as a result of the viscosity of the liquid. During a turn, the liquid in contact with the inside of the compass bowl tends to be dragged around with the bowl. Therefore, the liquid tends to swirl in the same direction as the aircraft's turn, and drag the magnetic assembly with it in the same direction. This results in the compass indicating an incorrect reading during a turn. Use the replay facility to become familiar with the effect of liquid swirl. Turning and straight line acceleration errors can be quite substantial in the direct reading compass. So we will devote the rest of the lesson to these errors and how we deal with them, starting with errors resulting from straight line or linear acceleration. So to begin, let's look at the effect of a straight line or linear acceleration on the compass reading, and then we will look at why the effect arises. Let's accelerate an aircraft on a heading of due west, or 270 degrees in the northern hemisphere. Watch the compass heading, and we can see that as the aircraft accelerates, the compass tells us we are turning to the right, even though the aircraft's true track has remained in a straight line. Now let's look at the reason why this error occurs. Linear acceleration errors occur in direct reading magnetic compasses because the magnet assembly is pendulously suspended. If the centre of gravity of the compass assembly is not directly beneath the pivot point, as we can see in the diagram here, a couple will be set up between the direction of acceleration and inertia acting through the centre of gravity, which results in a turning moment. As magnetic dip causes the pivot point and the centre of gravity to become misaligned, it follows that where a turning moment can be created by magnetic dip, a turning error will occur. Let's look again then, with the help of our diagrams, at an acceleration on a heading of due west, or 270 degrees in the northern hemisphere. Because of dip, we can see that the end of the magnet which is attracted to the nearest terrestrial magnetic pole, in this case the North Pole, hangs down below the horizontal. This means that the magnet's pivot point is no longer overhead the centre of gravity. Instead, we can see it is closer to the nearer pole. The acceleration acts on the pivot point. However, the reaction to the acceleration acts on the centre of gravity. This produces a turning moment or couple, which causes the compass needle to rotate, even though the aircraft is not turning. It is worth noting that where magnetic dip occurs, regardless of which hemisphere we are in, an acceleration always results in an apparent turn towards the nearest magnetic pole. In deceleration, the opposite rules apply, and deceleration always results in an apparent turn towards the magnetic equator whenever magnetic dip occurs. It follows also that except for a small amount of liquid swirl effect in turns, there will be no acceleration errors at the magnetic equator because there is no magnetic dip at the magnetic equator. There will be no acceleration errors on north or south headings either, as on these headings both the pivot point and the centre of gravity are in alignment with the aircraft's fore and aft axis. Let's look at turning errors now. Apart from the small error caused by liquid swirl, a turning error is an acceleration error, as any turn is effectively an acceleration in the direction of the turn. The basic theory is therefore the same as that for linear acceleration errors. Remember that acceleration errors occur where there is significant magnetic dip. Turning errors are maximum when turning through north or south. The error increases with magnetic latitude because magnetic dip increases. If liquid swirl is ignored, the errors will be zero when turning through east or west. Turning errors are usually more significant than linear acceleration errors for the following reasons. Turns are generally of greater magnitude, which results in a greater displacement of the magnet assembly. Turns occur more often and are likely to last longer than linear accelerations. Let's look at some actual examples of turning errors. Suppose we now consider what happens to the compass reading when an aircraft executes a left-hand turn from 045 degrees to 315 degrees through north in the northern hemisphere. To understand what happens, there are two things we have to bear in mind. The first thing to remember is that the example is in the northern hemisphere, and so the red end of the magnet will hang down below the horizontal because of magnetic dip. The pivot point of the magnet assembly will not therefore be over its centre of gravity. Instead, it will be nearer the red end of the magnet. During the turn, the magnet will be dragged to the left by the pivot point, while inertia will react through the centre of gravity. As these forces are not in line with each other, a couple is created which causes an anti-clockwise turning effect, moving the red end of the magnet to the left and the blue end of the magnet to the right, as we look at it here. The second thing we have to bear in mind, and this is fundamental to our understanding of turning errors, is that the compass rose card is orientated to enable the pilot to read the aircraft's heading directly from the compass card. This means that in order for the compass to read in the direction the pilot is facing, the compass card on the instrument will have to be orientated 180 degrees about the cardinal points of the compass. We can see this here, and it will help our understanding if this image is kept in mind. Remember that the compass card is fixed to the magnet, while the lubber line is fixed to the compass casing. So if the magnet swings anti-clockwise when viewed from overhead, the compass reading will increase, or overread. Conversely, if the magnet swings in a clockwise direction, the compass will decrease, or underread. Now let's return to looking at a left-hand turn from 045 degrees to 315 degrees through north in the northern hemisphere. Following the aircraft round the turn, we can see that although the aircraft has turned 90 degrees around the compass, during the same period of time, the magnet has rotated in the same direction by, say, only 70 degrees. Look closely, and we will see that only around 70 degrees have passed behind the lubber line and the compass overreads. In effect, the compass needs to catch up with the aircraft. So when the aircraft is on the desired heading of 315 degrees, the compass is indicating approximately 335 degrees. In order to turn the aircraft onto the desired heading of 315 degrees, therefore, the turn must be stopped when the compass reads 335 degrees or 20 degrees early. The compass will then catch up to read correctly. Think about it. Now let's look at what happens if we carry out a right-hand turn from 315 degrees to 045 degrees through north, again in the northern hemisphere. As before, because of magnetic dip, the red end of the magnet hangs down below the horizontal, and the pivot point will be nearer the red end of the magnet. The pivot point is no longer over the magnet assembly's centre of gravity. During the turn, the magnet will be dragged to the right by the pivot point. However, the inertia will react through the centre of gravity. As these forces are not in line, there will be a couple causing a turning effect, moving the red end of the magnet to the right. Although the aircraft has turned 90 degrees around the compass, the magnet has been rotated in the same direction by a small amount, say 20 degrees. We have only seen 70 degrees pass behind the lubber line, and the compass underreads. In order to stop on the correct heading of 045 degrees, the turn must be stopped on 025 degrees or 20 degrees early. Let's suppose we turn an aircraft to the right from 135 degrees to 225 degrees through south in the northern hemisphere. Once again, because of magnetic dip, the red end of the magnet hangs down from the horizontal, and as before, the pivot point will be nearer the red end of the magnet. The pivot point is no longer over the magnet assembly's centre of gravity. During the turn, the magnet will be dragged to the right by the pivot point. However, the inertia will react through the centre of gravity. As these forces are not in line, the couple created causes a turning effect, moving the red end of the magnet to the right. If the result of this is difficult to envisage, remember that we are now facing in a southerly direction in the northern hemisphere. Although the aircraft has turned 90 degrees around the compass, this time the magnet has been rotated in the opposite direction by a small amount, say 20 degrees. We see 110 degrees of heading change briefly, and the compass overreads. In order to stop on the correct heading, the turn must be stopped when the compass reads 245 degrees or 20 degrees late. By now, we should be able to work out on our own what happens when we turn from 225 degrees to 135 degrees in the northern hemisphere through south. Click on Continue when you have decided what compass heading you must stop the turn on. The answer is that we are turning left, and we should stop the turn when the compass reads approximately 115 degrees, or in other words, 20 degrees late. As before, because of magnetic dip, the red end of the magnet hangs down from the horizontal, and the pivot point will therefore be nearer to the red end of the magnet. The pivot point is no longer over the magnet assembly's centre of gravity. During the turn, the magnet will be dragged to the left by the pivot point. However, the inertia will react through the centre of gravity. As these forces are not in line, the couple created will cause the red end of the magnet to move to the left. As with the turn to the right, from 135 degrees to 225 degrees, we should stop the turn late. As a general guide to how soon or how late to stop a turn, it is worth noting that for a rate 1 turn, the turning error will be approximately 20 degrees. Rate 1 turns are commonly used in instrument flight, and in a rate 1 turn, it takes 2 minutes to turn through 360 degrees. For a rate half turn, allow a turning error of 10 degrees. And for a rate 2 turn, allow a turning error of 30 degrees. To conclude the lesson, this table summarises turning errors in the northern hemisphere. In the southern hemisphere, the errors are the exact opposite. The term sluggish, which appears in the right-hand column, means that the compass heading is lagging behind the aircraft heading. Liquid swirl will increase the turning error. Conversely, when the term lively is used, the compass heading is leading the aircraft around the turn. Liquid swirl in this case will reduce the turning error. The following rules apply. During a turn through the pole which is physically nearer the aircraft, the compass will be sluggish. It is therefore necessary to stop the turn early on the indications given by the direct reading compass. During a turn through a pole which is physically further from the aircraft, the compass will be lively. It is therefore necessary to stop the turn late on the indications given by the direct reading compass. At the magnetic equator, there is no dip. Therefore, the only turning error will be due to liquid swirl. Liquid swirl may account for a compass heading lag of around 5 degrees, or 5 degrees sluggish. Remember, it is the displacement of the magnets in a clockwise direction when viewed from above, which causes the compass to underread. A displacement in an anti-clockwise direction causes the compass to overread. This is the first of 3 lessons on the gyromagnetic compass. The gyromagnetic compass is an instrument which evolved out of the need to overcome the limitations of both the direct reading magnetic compass and the directional gyro indicator. We'll start by reminding ourselves of these limitations, and then go on to see how the design of the gyromagnetic compass removes or eliminates them. The direct reading compass has 3 major limitations. These are: firstly, turning and acceleration errors. The compass cannot be read accurately during a turn. Secondly, the magnetic sensing element. That is, the group of magnets on the vertical card is contained within the instruments and has to be situated close to the pilot so that the card can be seen. Unfortunately, the cockpit area is close to sources of deviation, such as electric lights, electric motors, and ferrous metal. Finally, it is a stand-alone system. The instrument is self-contained. It is not possible to take magnetic heading from it as an electrical or mechanical input into other equipment, such as those which display bearings from ground radio beacons, the autopilot, and the flight data recorder. The directional gyro indicator attempts to solve some of these problems by use of an air-driven or an electromechanical gyro. Turning and acceleration errors are eliminated, and outputs can be taken to other equipment, for instance, to display radio bearings. However, there is no magnetic input to the heading. There is no correction except by the pilot manually synchronizing to the direct reading compass at regular intervals. What is required is a system which combines the best of both. The short-term rigidity of the gyro overcomes turning and acceleration errors. This needs to be combined with the longer-term monitoring of the Earth's magnetic field, so that if the gyro starts to drift, a servo system slaves it back to alignment with a magnetic input. Such a system is called a gyromagnetic compass. The gyromagnetic compass is known by several names. It can be referred to as the gyromagnetic compass, remote indicating compass, slaved gyro compass, magnetic heading reference system. They all mean the same thing. A more modern version, which often includes other functions, such as the display of VHF omni-range, usually shortened to VOR, is known as the Horizontal Situation Indicator, or HSI. The system comprises the following elements: a magnetic detector unit. This is also often known as a flux valve or a flux gate. Note that it is usually mounted on a wingtip or on top of the fin, and is therefore well removed from most of the sources of deviation. A compass indicator dial. This is what most people refer to as the compass. A precession amplifier. This may also be known as a slaving amplifier. A precession motor. This may also be known as a slaving or synchronizing motor. And a horizontal gyro, similar in principle to the one used in the DGI. In simple systems, the horizontal gyro is directly connected to the compass card of the indicator dial through two cogs, which change the rotary motion through 90 degrees. This is called a bevel gear, and it works like this. We are assuming our gyro is connected to the compass indicator dial by a bevel gear in the description which follows. The purpose of the detector unit, or flux valve, is to sense the Earth's magnetic field and reproduce it within the compass indicator. We will explain how this is done later. At this stage, we'll just say that magnetic heading has been detected electronically and passed to the indicator in the form of alternating current, or AC. We'll also assume that the compass has already been initially synchronized, in order to make the gyro drive shaft output to be the same as the flux valve. Again, we'll cover how this is done later. In the compass indicator box, the flux valve output is compared with the position of the gyro drive shaft. This is the shaft which positions the compass card indicator, that is, the heading shown to the pilot. If the two are aligned, no further action takes place. The compass card is reading the right heading. We'll assume a steady heading, which gives a steady input from the flux valve. From this point, any difference between the flux valve field and the gyro alignment would only arise if the gyro were to drift. If this happens, the drive shaft will not be in alignment with the flux valve field, and an AC error signal is generated and passed to the precession amplifier, where it is amplified, phase detected, and rectified to direct current, or DC. The DC signal drives the precession motor, which turns the gyro. This gyro output is fed via the direct drive shaft to the HSI, for comparison with the flux valve signal. If the two are aligned, the compass is synchronized, and no further action takes place. If not, the error connection continues until the compass is synchronized. We now have a system in which if the gyro drifts away from the steady flux valve heading, it is brought back again by the precession amplifier and motor. We have explained the normal operation in terms of the gyro, which has a tendency to drift, being slave to the magnetic detector unit. However, there is also a smoothing of the signal the other way, because the magnetic flux valve signal itself is subject to short-term fluctuations, and the effect of these is reduced by the gyro. Let's see how. The magnetic field detected by the flux valve is generally stable over periods of tens of minutes or of hours, but it can fluctuate for short periods of up to 2 or 3 minutes, particularly during accelerations and turns. Suppose that, for some reason, the flux valve signal has temporarily introduced a small error. This will be compared with the gyro signal, and the error will be detected. The system has no way of telling whether the error is in the flux valve or the gyro, and so the error signal will start to drive the gyro to follow the flux valve. However, the precession motor is designed to take the error out slowly, correcting the gyro at a rate of only 3 degrees a minute, or thereabouts. The gyro will therefore respond slowly to this short-term error. The error may well disappear before the gyro has turned significantly. If not, as soon as the flux valve signal is correct again, the gyro will follow it back to the correct value. So, because of the choice of precession rate of the motor, any small short-term flux valve errors are damped out by the gyro's slow response. We therefore have a system which combines the best of both sources: the short-term rigidity of the gyro and the longer-term monitoring of the Earth's magnetic field. Now consider what happens in a turn. We will assume initially that the gyro does not drift during the turn, which may well be the case, because even during a full 360-degree orbit at the standard rate 1, the turn will only take 2 minutes. The aircraft turns, but the gyro, having rigidity, does not. This gives relative rotation between the horizontal gyro and the instrument case, and so operation of the bevel gear causes the direct drive shaft to rotate, changing the heading indication on the compass card. However, at the same time, the heading sensed by the flux valve, which is being passed to the drive shaft for comparison, is changing at the same rate. Therefore, no error signal is generated, and the compass should remain synchronized during the turn. If, in fact, there is some gyro drift during the turn, on completion of the turn there will be a small error signal. This will be taken out, as described in the previous scene. The use of a slow precession rate gives us a problem at startup. On initial switch-on, the alignment that the gyro takes up is random, and is unlikely to be in synchronization with the Earth's magnetic field. Therefore, an error signal is detected. The problem is that the precession motor's normal correction rate is designed to be only 3 degrees per minute, in order to smooth out short-term fluctuations, and if the gyro happened to be 90 degrees out, it would take 30 minutes to synchronize, which is obviously unacceptable. The solution is to have a rapid synchronization facility. This can either be a mechanical clutch operated by the pilot, as in the DJI, or, in later compasses, a high-gain mode for the precession amplifier, similar in principle to rapid erection in the electric artificial horizon. This is operated by a 2-position switch, spring-loaded to the normal position, which has to be held against the spring for rapid alignment. Operation of this switch increases the precession motor's correction rate, so that synchronization takes only a few seconds. More modern compasses are even more automatic. If a large error is detected, fast precession takes place at typically 60 degrees per minute until the error is 0. Then the system automatically reverts to the slow, smooth precession rate of typically 3 degrees a minute. We therefore have to modify our original block schematic to include the rapid synchronization facility. We still have 2 more lessons to come on the gyromagnetic compass, one on the flux valve and the other on the remaining components. But let's summarize what we've covered so far. The direct reading compass suffers from turning and acceleration errors. Is situated close to the pilot, but also to sources of deviation, such as electric lights, electric motors, and ferrous metal, and is a self-contained instrument. It is not possible to take magnetic heading from it as an electrical or mechanical input into other instruments. In the directional gyro indicator, turning and acceleration errors are eliminated, and outputs can be taken to other equipment. But there is no magnetic monitoring. We therefore have a system which combines the best of both sources: the short-term rigidity of the gyro and the longer-term monitoring of the Earth's magnetic field. We looked at all the basic components. This system has several advantages over the direct reading compass and DJI. Firstly, the flux valve is usually mounted on a wingtip or on top of the fin, and is therefore well removed from most of the sources of deviation. On initial switch-on, the gyro is brought into alignment with the signal detected at the flux valve. From then on, the outputs of the gyro and the flux valve are compared. If there is any error, the gyro is precessed into alignment with the flux valve by the precession amplifier and precession motor. This overcomes the normal gyro drift. The flux valve on its own would still suffer from turning and acceleration errors. But sending the signal via the gyro gives stability and rigidity, because the precession motor applies corrections to the drive shaft at the rate of approximately only 3 degrees per minute. In a turn, both the flux valve and the gyro shaft turn at the same rate, so there should be no significant error at the end of the turn. If any error is generated in the turn, it will be small, and is precessed out in the normal way after completion of the turn. Finally, we modified our block diagram to include the rapid synchronization facility. This concludes the lesson. We will look at flux valve theory in the next session. This is the second of 3 lessons on the gyromagnetic compass. In the last lesson, we established the need for the gyromagnetic compass, and we showed the basic components which make up the system. We said that the purpose of the detector unit, or flux valve, is to sense the Earth's magnetic field and reproduce it within the compass indicator. The detector unit is positioned in a part of the aircraft least affected by onboard electrical fields. This is usually the wingtip or tail fin, where any aircraft-generated magnetic disturbances are at a minimum. This is a typical detector unit. The circular plate is screwed to the underside of the wing. The black hemisphere protrudes out into the airflow, and is simply a protective cover for the flux valve inside. The cable carrying the signals passes along inside the structure of the wing. The primary component is the flux valve, a 3-spoke device, shown in red here to make the spokes obvious. In fact, they are a silvery metal colour. The 3 spokes on their own look like this. The flux valve is pendulously mounted on a device known as a Hooke's joint, which enables the detector to swing within limits of 25 degrees about the pitch and roll axes. This is to allow the flux valve to hang level, even if the aircraft pitches and banks up to 25 degrees. However, the Hooke's joint allows no rotation in azimuth. This is because the flux valve must follow the direction of the aircraft's heading. The curved ram's horns at the end of each of the 3 legs are simply to improve magnetic flux gathering efficiency, but they do not affect the principle. The flux valve would detect the Earth's magnetic field even without them. To explain how the flux valve works, we will start by considering just a single leg, without the curved part on the end. Alternating current is fed to the coil wound around the centre post, which in turn produces fields of opposite sign in the top and bottom legs of the flux valve. The magnetic flux, which is a measure of the density of the lines of force in legs A and B, is shown here as red and blue lines. They are at the same frequency and amplitude, but are in antiphase. Note that the pick-off coil is wound around both of the legs A and B, and so their effect will be added. If we add the components A and B together, the resultant flux, which is shown here by a green line, is therefore 0, and so no current is induced in the pick-off coil. So far, we have been looking at the coil in isolation, without considering the Earth's magnetic field. However, if the flux produced by the Earth's magnetic field were present as a background, the positive and negative flux would start from a different baseline, which would not be 0. Therefore, they would be shifted up like this. But the physical characteristics of the metal used in the flux valve legs are such that it magnetically saturates at a certain level. The metal will not magnetize further beyond this. This causes the curve to top out at a limiting saturation level, giving the flattened response shown here. Now when we add the total flux from both legs A and B together, The resultant follows the path of the green line. The operation of the flux valve is in accordance with Faraday's law of electromagnetic induction, which states that if the number of lines of force threading a circuit is changing, an induced electromotive force will be set up in the circuit, the magnitude of the EMF being proportional to the rate of change in the number of lines of force threading the circuit. So the secondary winding, the one coloured red here, will pick up change in magnetic flux density, that is, the dips in the green line, as an EMF. This will be detected as an AC signal. Therefore, if our coil round the legs of our flux valve spoke is pointing northwards, it is in line with the Earth's magnetic field, and will pick up an EMF. However, if it were pointing eastwards, it would be pointing at 90 degrees to the Earth's magnetic field, and would not detect anything. So the voltage from the flux valve spoke depends on the direction of the spoke relative to the Earth's magnetic field. It is a function of the cosine of the magnetic heading. Unfortunately, we cannot simply measure the voltage and work out our heading, because, except for 0 and 180 degrees, there are two possible values of heading for each value of voltage. Also, if there were any slight change of input voltage, it would give an altered value of output voltage, resulting in a different measured heading. Instead, we use 3 spokes in the flux valve, and the output from each leg is fed to one of the 3 coils, which are situated around the direct drive shaft in the compass indicator. These coils are called stators. Each spoke of the flux valve senses a different voltage, because they are spaced 120 degrees apart, and therefore make a different angle to the Earth's magnetic field. These 3 different voltages are passed to the respective legs of the stator. This creates an AC field in the direction of the aircraft's heading around the direct drive shaft. We now have to detect this. We do this by inserting a device called a rotor into the centre of the stators. It is a wound coil mounted on the gyro drive shaft. If the coil is in line with the AC field generated by the stators, a secondary AC voltage will be induced in the rotor. However, if the rotor is at 90 degrees to the AC field, no secondary voltage is induced. This is known as the null position. At any position other than the null, some secondary voltage is induced. This is the error signal which we covered in the first lesson. These are not complicated ideas, but this is quite a lengthy sequence. So if you want to go through it again, click on the Replay Scene button. This secondary induced voltage is passed to the precession amplifier, where it is amplified, phase detected, and rectified to DC. The reason for the amplification is fairly obvious, that the unamplified error signal is not powerful enough to drive the precession motor. The purpose of phase detection is to detect the sense of the error. It is important that the precession motor knows which way to turn. Suppose that the gyro shaft is misaligned 2 degrees clockwise from the null. The motor should rotate the shaft 2 degrees anti-clockwise, not all the way round 358 degrees clockwise. Otherwise, the system will go into continuous rotation. Finally, it has to be rectified. This is because the mechanism of the precession motor is a DC torque motor. Therefore, a change in polarity causes a reversal of rotation. The error signal continuously drives the precession motor at the slow precession rate of around 3 degrees a minute, until the rotor reaches the null position with respect to the stators. Let's summarize what we've covered in this lesson. The magnetic detector unit is positioned in a part of the aircraft least affected by onboard electrical fields. This is usually the wingtip or tail fin, where any aircraft-generated magnetic disturbances are at a minimum. The primary component is the flux valve, a 3-spoke device. The flux valve is pendulously mounted on a device known as a Hooke's joint, which enables it to hang level even if the aircraft pitches and banks up to 25 degrees. However, the Hooke's joint allows no rotation in azimuth. This is because the flux valve must follow the direction of the aircraft's heading. We showed that the output of a single spoke of the flux valve is a function of the cosine of the magnetic heading. But, because of ambiguity, we use 3 spokes in the flux valve, and the output from each leg is fed to one of 3 stators. This creates an AC field in the stators around the direct drive shaft. A rotor is mounted on the gyro drive shaft. If the coil is not at 90 degrees to the AC field generated by the stators, an error signal drives the rotor to the null position. The error signal has to be amplified, phase detected, and rectified to DC. The error signal continuously drives the precession motor at the slow precession rate of around 3 degrees a minute, until the rotor reaches the null position with respect to the stators. This concludes the lesson on the flux valve. The next one will look at the remaining components of the gyromagnetic compass, and also how magnetic heading is transmitted to other instruments.
This is the third of 3 lessons on the gyromagnetic compass. Previously, we have established the need for the gyromagnetic compass, and we showed the basic components which make up the system. We also showed how the detector unit, or flux valve, senses the Earth's magnetic field and reproduces it within the compass indicator. We are now going to examine some of the components more closely and also add some new ones. The first one to look at in more detail is the compass indicator dial. Here is a typical modern compass indicator dial. As we know, the compass card is directly driven by the shaft from the gyro. It rotates as heading changes, and the heading is read against the index line in the 12 o'clock position, which is sometimes called the lubber line. A desired heading can be selected by the pilot by rotating the heading selector control. The heading select marker, usually called a bug, indicates the selected heading. If the magnetic input from the flux valve fails, a warning is given in the form of a heading warning flag. Depending on the level of sophistication of the particular model, there may well be other facilities and warnings, particularly if it is a modern horizontal situation indicator, or HSI, which is also used to display VOR and ILS information. However, these will be covered in radio navigation and are not discussed further here. If the magnetic input from the flux valve should fail, or if it becomes unreliable due to proximity to one of the Earth's magnetic poles, it is possible to operate the gyromagnetic compass in gyro mode only. If this happens, it acts as a DGI and will need to be reset periodically to a directional reference, such as a standby compass or other source of aircraft heading. When it operates as a DGI, this is referred to as free mode, whilst its normal magnetically monitored operation is referred to as slaved mode. This is a typical modern compass controller. With the free/slave switch at slave, the compass operates in the normal magnetically monitored mode. If the switch is moved to free, the magnetic signal from the flux valve is disconnected, rotor-stator comparison ceases, and the gyro is no longer tied in azimuth, and so acts as a free gyro, exactly like a DGI. When it is being used in free mode, The pilot adjusts the indicated heading in order to correct it to an external datum heading with a switch, which is spring-loaded to the central position. During normal flight in slave mode, there is usually continuous slight motion due to oscillations of heading and to vibration, which means that rotor-stator comparison of the magnetic flux valve signal against the gyro shaft position continuously generates very small error signals. The error signal, and therefore the precession amplifier, are continuously hunting. This is normal, and is how the system is designed to work. These error signals pass through a voltmeter called an annunciator, on their way from the amplifier to the precession motor. The annunciator looks like this. Normal operation results in continuous slight oscillation of the vertical line about the central position. The annunciator is useful to the pilot for two main reasons. It is an indication that magnetic monitoring of the gyro is taking place. It shows that the compass is synchronized. And on systems where it is necessary for the pilot to synchronize manually on startup, or after a desynchronization, it indicates which way to turn the compass. Gyro wander can take two forms: drift and topple. The tendency to drift is overcome, as already described, by slaving the gyro to the flux valve output, thereby making it a tied gyro in azimuth. However, the gyro would still topple, over a period of time, unless prevented from doing so. It therefore needs to be tied either to the aircraft yaw axis or to gravity in order to keep it erect. Both the yaw axis and the vertical, as defined by gravity, have been used as the datum in various models of compass. Both systems use a levelling switch and a torque motor. To tie the gyro to the yaw axis, the inner and outer gimbals are maintained at 90 degrees to each other by a system of commutators, insulating strips, and brushes. If the gyro topples, the brushes are no longer in contact with the insulating strip, so a current passes through the commutators. Alternatively, to tie the gyro to the vertical, mercury gravity switches are used. Either way, the correcting signals are passed to a torque motor, which applies a rotational force to the gyro in the yaw axis. The resulting precession causes the gyro to return to the horizontal, but at a slow precession rate, so that it does not react wildly to temporary departures from the horizontal, such as turns, accelerations, climbs, and descents. One of the advantages of the gyromagnetic compass over the simple direct reading compass is the facility to electrically transmit heading information to use as an input into other instruments such as the RMI, autopilot, and flight data recorder. The information is picked off from the drive shaft between the gyro and the compass card. The transmitting and receiving device is called a cell-SYN unit. The word cell-SYN is short for self-synchronization. A second rotor and set of stators is inserted into the direct drive shaft between the gyro and the compass indicator dial. This is the transmitter unit of the cell-SYN unit, and is nothing to do with part of the flux valve transmission to the drive shaft. The orientation of the cell-SYN unit rotor is therefore the heading which is to be transmitted. The rotor is supplied with a constant primary excitation AC voltage, which induces a field in the stators. The stators are directly connected by 3-strand wire to the 3 stator arms of the repeater, so an identical field is reproduced there. As many receivers as are required can be attached. If the rotor of the repeater is not perpendicular to the field in the repeater stators, an AC voltage will be induced in this repeater rotor. This is passed to an amplifier and then to a motor to turn a shaft on which the repeater rotor is mounted. The repeater shaft will turn until no further voltage is detected. The repeater shaft therefore follows any heading changes in the main gyro drive shaft. The receiver shafts are 90 degrees out of phase with the transmitter because the transmitter field is induced in line with its rotor, but the receiver rotors adopt the null position. However, this is easily solved by offsetting the indicator dials by the required amount. Let's summarize this lesson. Compass indicator dials vary with the vintage and the sophistication of the compass, but most have a rotating compass card with the heading indicated by the lubber line index at the 12 o'clock position. Additionally, they all have, in some form or other, a heading selector, a heading bug, and a warning flag if the magnetic input fails. If the magnetic input from the flux valve should fail, or if it becomes unreliable due to proximity to one of the Earth's magnetic poles, it is possible to operate the gyromagnetic compass in gyro mode only. This is known as the free mode. It is operating as a DGI. The pilot must then adjust the indicated heading periodically in order to correct it to an external datum heading. The annunciator tells the pilot that the compass is synchronized. And on systems where it is necessary for the pilot to synchronize manually on startup, or after a desynchronization, it indicates which way to turn the compass. In order to prevent topple, the gyro needs to be tied to the aircraft yaw axis, or to gravity in order to keep it erect. The gyromagnetic compass can be used to transmit heading information to other instruments. This is done by a Celsin unit, in which the transmitter is a stator-rotor combination, with the rotor on the compass indicator driveshaft. The receiver or receivers are another stator and rotor combination, in conjunction with an amplifier and an electric motor. This completes all the lessons on the gyromagnetic compass.
In this lesson, we are going to look at aircraft magnetism, how it is acquired, and how it affects the accuracy of the magnetic compass. We will look at a compass wing and how a compass wing can remove or reduce the errors caused by aircraft magnetism. To conclude, we will look at the occasions when a compass wing should be carried out. The phenomenon which gives rise to the aircraft's own magnetic field is known as aircraft magnetism. Aircraft magnetism is acquired during the manufacturing process and subsequent use of the aircraft. It is caused by a combination of ferrous metals and electrical fields within the aircraft. Magnetism can be divided into hard iron and soft iron. Hard iron can be considered to be permanently magnetized and will make up the permanent magnetic field of the aircraft, whereas magnetism in soft iron will be induced only while there is an external magnetic force present. In theory, a magnetic compass should align itself with the Earth's magnetic field and point to magnetic north. However, an aircraft's own magnetic field will attract the magnetic compass away from magnetic north. The direction in which the magnetic compass points as a result is known as compass north. The angle between compass north and magnetic north is known as the deviation. Let's look at the effect of deviation. Suppose we imagine an aircraft is flying on a heading of 090 degrees in relation to true north. If the magnetic variation is 10 degrees west, the heading in relation to magnetic north will be 100 degrees. If we now say that deviation is 10 degrees west also, the compass will be showing 110 degrees as a heading. So to recap, deviation is defined as the angular difference between the direction actually indicated by a compass needle and magnetic north. Deviation is classed as easterly or positive, or westerly or negative, depending on whether the compass needle lies to the east or west of magnetic north. If we were to assume that deviation was 5 degrees east instead of 10 degrees west, the compass heading in our example would be 095 degrees. It is possible to remove a large amount of deviation error by appropriate calibration and correction of the compass. This process is called a compass swing, which we will look at next. To work out the amount of deviation being experienced, the aircraft's magnetic compass reading is compared with a magnetic datum compass. The comparison process is known as the compass swing, and the compass swing is carried out on an airfield in a location specifically designed for this operation. We can see the principle of the compass swing here. Initially, the datum compass and the aircraft compass are aligned with each other. The aircraft is then turned through 90 degrees. The compass heading is compared with the datum compass reading and the observed deviation recorded. The process is then repeated through 180 degrees and 270 degrees. The aims of the compass swing are: firstly, to observe and determine the deviations between magnetic north and compass north on a series of headings. Secondly, to correct and remove as much deviation as possible. And thirdly, to record the residual deviation which is left after a compass has been adjusted. Unfortunately, magnetic influences on the aircraft's magnetic compass are distributed all over the aircraft. Individually, they'd be hard to locate and identify, so the solution is not necessarily to identify them, but merely to establish their total effect on the aircraft's magnetic compass reading. The total effect can be split into a longitudinal component and a lateral component. Deviation will vary with heading. Let's see why this occurs. Imagine that all of the aircraft magnetism is combined into a single isolated blue pole, which by definition will attract the red end of the aircraft's compass needle. Remember, like poles repel each other, unlike poles attract. Let us locate this blue pole on the longitudinal axis of the aircraft and in a position which is forward of the aircraft's compass. If we also create a graph, we can plot the deviation caused by the blue pole as we rotate the aircraft through 360 degrees. So let's look first at the effect the blue pole will have when the aircraft is heading north. The blue pole and the red end of the compass needle are aligned with the Earth's magnetic field, and so there'll be no deviation. Let's see what happens now if we turn the aircraft onto a compass heading of 045 degrees. The blue pole is now out to the east of magnetic north, and so the compass needle will point, or be deviated, to the east. As the aircraft turns onto a compass heading of 090 degrees, the blue pole is even further out to the east. On this heading, the deviation effect has increased to a maximum because, if our aircraft now continues to turn onto a compass heading of 135 degrees, we can see that the blue pole is far less out to the east and the deviation has reduced accordingly. When the aircraft turns onto a compass heading of 180 degrees, the blue pole is directly opposite magnetic north, but because its effect is less than the Earth's magnetic field, there will be no deviating effect. Continuing the turn, deviation now becomes westerly, increasing to a maximum on a compass heading of 270 degrees, before reducing back to zero on magnetic north. Looking at the graph, we can say that the contribution to deviation from longitudinal aircraft magnetism is a function of the sign of the heading. The combined longitudinal hard and soft ion component of aircraft magnetism is known as coefficient B. Let's suppose we now locate the blue pole on the lateral axis of the aircraft, out on the right wing, and repeat the turn through 360 degrees. There is a maximum easterly deviation, with the aircraft heading north, as we can see. Following this through a 360-degree turn in a clockwise direction will result in a positive cosine curve. We can therefore say that the contribution to deviation from lateral aircraft magnetism is a function of the cosine of the heading. The combined lateral hard and soft ion component of aircraft magnetism is known as coefficient C. In practice, both longitudinal and lateral elements will be present and will combine to form the total deviation. We can therefore formulate an equation to calculate deviation on any heading, if we include one further factor. This factor is simply the contribution made to the total deviation should the aircraft compass be physically misaligned with the longitudinal axis of the aircraft, and it is known as coefficient A. The equation is therefore deviation on any heading equals coefficient A plus coefficient B sine heading plus coefficient C cosine heading. Coefficient B is the combined longitudinal hard and soft ion component of aircraft magnetism, and coefficient C is the combined lateral hard and soft ion component of aircraft magnetism. Let's work through an equation. So let's suppose coefficient A is plus 2 degrees and coefficient B is plus 3 degrees. And coefficient C is minus 4 degrees. And we will say the compass heading is 060 degrees. The total deviation on 060 degrees equals 2 degrees plus 3 degrees times sine 60 degrees minus 4 degrees times cosine 60 degrees, which equals 2 degrees plus 2.59 degrees minus 2 degrees equals plus 2.59 degrees. If we approximate 2.59 degrees to, say, 2.5 degrees, and if the pilot is flying a compass heading of 060 degrees, the magnetic heading is actually 062.5 degrees magnetic. Note that the deviation is applied in the sense that it is the correction required to convert compass heading to magnetic heading. If deviation is positive, magnetic heading is greater than compass heading. Error due to coefficient A is removed by turning the compass to realign the lubber line with the fore and aft axis of the aircraft. Let's say the error is plus 2 degrees. Error due to coefficients B and C are removed or minimized by creating local magnetic fields with additional magnets which are equal and opposite to the aircraft's magnetic field.
Coefficient B is removed on headings of east and west. Let's say the error is +4 degrees. And coefficient C is removed on headings north and south, because as we saw from the graphs earlier, the relevant coefficients will be at their maximum on those headings. Let's make the error due to coefficient C -2 degrees. However, it is unlikely that all the deviation will be removed by this process, and therefore any residual deviation will be recorded on a compass deviation card, which will be placed adjacent to the aircraft compass. We can see a typical example here, and we can see that the compass is indicating 270 degrees or west. The compass heading is the magnetic heading plus or minus the deviation on that particular heading. So the deviation card is telling us that to fly an accurate heading of 270 degrees magnetic or west, we should steer a compass heading of 269 degrees. In accordance with EU OBS, residual deviation limits are as follows. For the direct reading magnetic compass, it is plus or minus 10 degrees. And for the remote reading magnetic compass, it is plus or minus 1 degree. Aircraft magnetism is influenced by the Earth's magnetic latitude and will actually change as magnetic latitude changes. Let's see why this is by looking at the effects of the Earth's magnetic field on hard iron and soft iron as latitude changes. Earlier, we saw that hard iron magnetism can be regarded as permanent magnetism and is not affected by external fields. So if aircraft magnetism due to hard iron does not change, what is it that causes deviation to change as latitude changes? The answer lies in the relative strengths of the Earth's Z and H components. We know from the lesson which dealt with magnetic dip that the Z component of the Earth's magnetic field will be at its weakest at the Earth's magnetic equator and strongest at the magnetic poles. Conversely, the horizontal component of the Earth's magnetic field, which we called the H component, reduces as the Z component increases. In other words, the H component will be at its strongest at the Earth's magnetic equator and at its weakest at the magnetic poles. Let's look at the effect this will have on deviation. We know that aircraft magnetism due to hard iron can be assumed to be constant, and we can represent this constant by the blue line here. As the directional strength of a compass needle is governed by the strength of the Earth's H component, represented here in red, we can see that deviation will be low near the equator, but will increase towards the pole as the effect of the H component decreases. We can say therefore that with hard iron, aircraft magnetism does not change with magnetic latitude, but deviation will change with magnetic latitude. Let's look at soft iron now. We know that in soft iron, magnetism will be induced when there is an external magnetic force present. This includes the Earth's magnetic field, and in particular, the effect of the vertical, or Z component of the Earth's magnetic field on the aircraft magnetism. As we know, the Z component will decrease and the H component will increase towards the magnetic equator. We can see therefore that deviation due to soft iron will be greater as magnetic latitude increases. Firstly, because the strength of the Z component increases, and therefore the aircraft magnetism increases. And secondly, because the horizontal influence of the Earth's magnetic field decreases, other external influences will have a greater deviating effect. We can say therefore that with soft iron, aircraft magnetism changes with magnetic latitude, and deviation changes with magnetic latitude. There are a number of occasions when a compass swing will become necessary. They should be noted, and they are: 1. When the compass components are installed or replaced. 2. Whenever accuracy of the compass is in doubt. 3. After a maintenance inspection if required. 4. After significant aircraft modification, repair or replacement involving magnetic material. 5. When carrying unusual ferromagnetic payloads. 6. When the compass has been subjected to significant shock. 7. After the aircraft has been given a new location to operate in, if the move involves a large change of magnetic latitude. 8. If the aircraft has been parked in long-term storage on a single heading. 9. In the event of a lightning strike. 10. After significant modification to aircraft radio and electrical systems. This concludes the lesson on aircraft magnetism. A summary of the main points follows. A summary of the main points of the lesson is: deviation is classed as easterly or westerly depending on whether the compass needle lies to the east or west of the magnetic north meridian. The resulting direction in which the magnetic compass points is known as compass north. The aims of the compass swing are A. To observe and determine the deviations between magnetic north and compass north on a series of headings. B. To correct and remove as much deviation as possible. And C. To record the residual deviation which is left after the compass has been adjusted. The contribution to deviation from longitudinal aircraft magnetism is a function of the sign of the heading. The contribution to deviation from lateral aircraft magnetism is a function of the cosine of the heading. Deviation on any heading equals coefficient A plus coefficient B sine heading plus coefficient C cosine heading. Coefficient A is the contribution made to the total deviation should the aircraft compass be physically misaligned with the longitudinal axis of the aircraft. Coefficient B is the combined longitudinal hard and soft iron component of aircraft magnetism. Coefficient C is the combined lateral hard and soft iron component of aircraft magnetism. The regulatory residual deviation limits are plus or minus 10 degrees for a direct reading compass and plus or minus 1 degree for a remote reading compass. Hard iron aircraft magnetism does not change with magnetic latitude, but deviation does change. Soft iron aircraft magnetism changes with magnetic latitude, and deviation changes with magnetic latitude. The occasions when a compass swing may be necessary should be noted.
The navigation and flight management system of all modern airliners is based on the principle of inertial navigation. The inertial navigation system, which is usually abbreviated to INS or sometimes IN, began to be fitted to airliners in the late 1960s and early 70s. Those basic INSs have evolved into the more modern inertial reference systems. These are usually abbreviated to IRSs. Their technology and engineering has moved on 40 years, but the basic principles remain exactly the same as those of the early INS. INS is a complex and expensive full navigational aid. It is extremely accurate. It is independent of outside communications and ground stations. Consequently, it can operate worldwide. INS uses a sophisticated form of dead reckoning. It starts from a known position. It then measures and processes the accelerations of the aircraft. These accelerations give accurate data on speed and change of direction to determine a new position. In order to illustrate the principles of operation, we are going to look at 1970s style technology of INS. However, later lessons will develop these ideas to go on to the more modern IRS. INS measures or calculates the following navigational information: present position, that is, latitude and longitude; heading, which way the aircraft is pointing; track, the direction of the aircraft's path over the ground. The difference between heading and track is called drift. It is caused by crosswind. Ground speed, that is, the speed over the ground, which is usually not the same as the speed through the air. Again, this is the effect of wind. The INS also gives waypoint steering. This is the facility to enter a route as a series of latitudes and longitudes, and then have a steering signal generated to be displayed on the flight director system and fed to the autopilot. With waypoint steering, the INS will display the desired track between any two waypoints. For instance, the desired track between waypoint 1 and waypoint 2 in this example is 037 degrees true. It also calculates distance to go to the next waypoint and time to go. And it offers two other facilities, again, both associated with a desired track between two selected waypoints. The first is called cross-track displacement, and the second is track error angle. We'll explain these. This is a diagram of cross-track displacement. The INS has been programmed to steer the aircraft between waypoints 3 and 4. However, for some reason the IN has been disconnected from the autopilot and the aircraft has been flown out to the right of track, either manually or by taking a heading steer off the flight director. This could be, for instance, as a result of a mandatory air traffic control instruction. The INS can calculate the centre line of the route between the two waypoints and display the information that we are, in this case, 12.0 nautical miles to the right of the desired track. However, the word track can have another meaning. As well as being the path of the aircraft over the ground, it can also mean the direction of that path. Strictly speaking, this should be called track angle, but most people refer to it as just track. So, track error angle is not about whether you are a distance left or right of the desired track path. It is the difference between the desired track angle and the track angle you are flying at the time. Your actual track angle is the combination of your heading and your drift. If you are following the INS steer, the desired track angle and the actual track angle should be the same. However, if you have had to deviate from following the steers, again, possibly because of a mandatory air traffic control instruction, the two will not be the same. The difference is known as track error angle. In addition to all of these facilities, INS also generates roll and pitch data for attitude instruments. It is often assumed that the most important single advantage of INS over previous systems is that it produces a continuously computed present position with no dependence on external references. However, what is almost as important is that in order to compute this position, it was necessary to greatly improve heading measurement accuracy. INS heading is about 10 times more accurate than previous systems, which were gyromagnetic compasses. Additionally, INS heading is not dependent on Earth magnetism. INS calculates an initial true heading by detecting the Earth's spin, then relies entirely on high-grade gyros to maintain that accuracy. This will be explained later. INS can therefore be used for high latitude and polar navigation where the Earth's magnetic field may be weak or the value of variation may be unreliable. There are 3 basic units in the INS. 2 of them are on the flight deck and are operated by the pilot. The third can be remotely located in the aircraft and does not have to be accessed in flight. The 2 components located on the flight deck are the Mode Selector Unit, often abbreviated to MSU, and the Control and Display Unit, often called the CDU. The third unit contains inertial sensors and reference devices. As we shall shortly see, these sensors are accelerometers and gyros. This box is called the Inertial Navigation Unit, which is often shortened to INU. We will now look at the principle of operation. When an aircraft flies, there are 3 effects of motion. These are position change, velocity, and acceleration. Of these, only one can be detected without external reference. You cannot measure position or velocity from equipment entirely contained within the aircraft, using no radio or radar, but you can measure acceleration. Imagine a pendulum with the weight concentrated in the bottom, mounted in an aircraft. If the aircraft accelerates, the weight swings backwards. If the aircraft decelerates, the weight swings forwards. However, we're using the words forwards and backwards in relation to the aircraft. But it is the aircraft which is changing its motion, not the pendulum. Let's go back to basics. The weight at the bottom of the pendulum is obeying Newton's first law of motion. Every body remains at rest or in uniform motion unless acted upon by an external force. Suppose that the weight and the aircraft are both travelling at 400 knots. Now the aircraft accelerates to 410 knots, but the pendulum weight, at least initially, remains at 400 knots. It appears to us that the weight is swinging backwards, but in fact the weight is maintaining uniform motion. The aircraft is accelerating ahead of it. The weight therefore has inertia, and we can use it to measure the acceleration. This is why it is called an inertial navigation system. The measuring device is called an accelerometer, and the acceleration it measures is with respect to inertial space, not local gravity. Newton's laws of motion are universal, not Earth-orientated. The measurement of acceleration would work even if gravity were not present. In fact, inertial navigation is used for spacecraft. Therefore, the acceleration, when suitably processed, gives a measurement of ground speed, not airspeed. By knowing where we were when we started and adding up how far we have gone, we can work out where we are now, rather like the odometer of a car. It is not enough to simply measure accelerations. They have to be converted, firstly, into velocities, and then, secondly, into distance gone, in order to find the new present position. Each of these processes is called integration. You will have already come across it if you have studied integral calculus previously. For INS, as we said, we have to integrate twice. First, to convert the accelerations into velocities. Secondly, to convert the velocities into distances. As pilots, we're not required to understand calculus. We simply need to know that there are electronic devices that can carry out these processes for us. They are called integrators, and they are used in INS. This is a diagram of a Miller integrator, which was used in the 70s and is from the period of the equipment that we are looking at. However, these days it will be done digitally. Let's summarise what we've covered so far. INS is a complex and expensive full navigational aid. It is extremely accurate, independent of outside communications and ground stations, and can operate worldwide. INS provides much more than just present position. All of these facilities are measured or calculated. INS heading is about 10 times more accurate than previous gyromagnetic compass systems and is not dependent on Earth magnetism. It can therefore be used for high latitude and polar navigation, where the Earth's magnetic field may be weak or the value of variation may be unreliable. The basic units of the INS are the Mode Selector Unit, or MSU, the Control and Display Unit, or CDU, and the Inertial Navigation Unit, or INU. Accelerometers measure accelerations, which are integrated first into velocities, then into distance gone. By knowing where we were when we started and adding up how far we've gone, we can work out where we are now.
We previously established that the Inertial Navigation System, or INS, starts from a known initial position and, by continuous measurement of aircraft accelerations, keeps updating itself to the present position. We also said that it gives a great deal more information than just a present position, latitude and longitude. The accelerations are detected by a device known as an accelerometer. They are then converted, firstly into velocities, and secondly into distances gone by integrators. We are now going to examine this measurement and integration process more closely. We'll start by looking at accelerometers in a bit more detail. There are various different forms of accelerometer, but a popular early model was the pendulous E and I bar type. The E and I bar is a fairly common form of transducer, and is also found, for instance, in the servo-assisted altimeter, which you have already studied. The E bar is made of a material with a high magnetic permeability. This means that it responds by producing a high magnetic flux density in proportion to the inducing field, and responds rapidly to rapid changes in the inducing field. A source of primary current is applied through a coil winding round the centre leg of the E bar. If it were DC, this would convert the bar into an electromagnet, with a static north pole at one end and a south pole at the other. However, the primary exciter source is AC, usually at 400 Hz, and so the effect is that the magnet changes polarity every 400th of a second, that is, north to south and back to north again. Secondary windings on the outer two legs of the E-bar therefore experience a change of magnetic flux and pick up secondary AC voltages, the same principle as a transformer. The amount of induction in the secondary legs is affected by the gap between the E-bar and the I-bar. The I-bar is attached to a rigid pendulum and hangs vertically when there is no lateral acceleration. If the gap is the same, then the amplitude of the voltage induced at the two ends will be identical. But the polarity will be opposite, because when one end is a north pole, the other is a south pole, and vice versa. The positives and negatives cancel each other out, and we get a resultant of 0. However, if the whole accelerometer now experiences an acceleration, in this example to the right, the pendulum will swing to the left. Now the gaps at each leg of the E-bar are not the same, because the I-bar has been displaced. Therefore the induction at each end will be different. This will affect the amplitude, but not the polarity or phase. The positive and negatives will no longer cancel out, and there will be a resultant, which will be a new sine wave. This secondary induced voltage is passed to a feedback amplifier, where it is amplified, phase detected and rectified to DC. The DC is then passed to solenoids, which act as electromagnets, and attract a permanent magnet in such a sense as to re-centralize it. A voltage is picked off and measured downstream of the amplifier. This voltage will be proportional to the restoring force, and therefore the initial acceleration. By measuring the amplifier output voltage, we have a measure of lateral acceleration. Although the principle of the pendulous E and I bar accelerometer is as described, the actual mechanization does not need a long vertical bar, and practical accelerometers are usually a rectangular shape with the long side horizontal. We will represent them like this in future diagrams. Integrators convert a rate of change over a period of time into total amount of change over that time. If the input is acceleration, which is a rate of change of velocity, then the output is change of velocity. If the input is velocity, which is a rate of change of position, then the output will be change of position, which is another way of saying distance gone. Most modern INS integrators use digital computing. Suppose that over a second, the output from the accelerometer is an analog voltage like this. The integrator digital sampler will turn it into this. The input of acceleration, for example, is sampled many times per second, and each instantaneous value is multiplied by the time interval between samples. Adding all of these multiplied values together gives the total increase in speed over 1 second. Integration is a process of successive minute additions to, or subtractions from, the last known value to create a new value, in very small increments, but very frequently. We use two accelerometers in INS. They are mounted in such a way that one is always kept pointing towards true north. When its accelerations are integrated and processed, we get latitude. The other one is kept pointing true east. When its accelerations are integrated and processed, we get longitude. The accelerometers are mounted on a table that can rotate, called a platform. The platform is shown, obviously out of scale to the aircraft, for the sake of clarity. Suppose the aircraft is initially flying north. The orientation of the platform and the accelerometers will be such that the accelerometers have their sensitive axes facing north and east. Now suppose that the aircraft alters heading 45 degrees to the right. The platform servos have to turn 45 degrees to the left with respect to the airframe. The result is that the platform remains orientated to the north. This is one of the corrections to the platform for aircraft maneuvers. There are also corrections for pitch and roll. If, for instance, the airframe is pitched 5 degrees nose up, the front of the platform must be driven 5 degrees downwards with respect to the airframe. If the left wing is dropped, the platform must be driven upwards on that side to keep it level with the ground. The platform has motors in pitch, roll and yaw. For the INS to work, the response and correction to any sense manoeuvre has to be near real time, and the accuracy has to be better than 1/10 of a degree in all 3 planes. Additionally, the platform, which contains 2 accelerometers and 3 gyros, is quite heavy. The design of the platform servos was a demanding engineering challenge. Because of their mechanical complexity, the early platform servos had a limited mean time between failures. This was one of their known weaknesses, and it is one that has been overcome in the later inertial reference system. The information flow in INS is organized into 2 channels, a north-south channel and an east-west channel. Each accelerometer senses accelerations, one in the north-south sense. These accelerations are labelled A subscript n here. If the aircraft accelerates southwards, that is simply a negative north acceleration. The other accelerometer senses its accelerations in the east-west sense, which are labelled A subscript E here. If the aircraft accelerates westwards, that is simply a negative east acceleration. The northerly acceleration passes through the first stage integrator, where it is integrated into velocity northwards, v. You might think that if we have used the convention A subscript n for northerly accelerations, to be consistent, we should use v subscript n for northerly velocities, but we don't. In navigation, v on its own usually means northerly velocity, and u on its own means easterly velocity. It is a widely used convention, and we will follow it. The easterly acceleration is converted by its integrator into velocity eastwards, or u. These velocities will be integrated again shortly into distance gone, but even at this stage we can use them to get track and ground speed. The north and east velocities are passed to a compounder. A compounder is simply a computing device for taking velocities which have been resolved in two directions at 90 degrees to each other and calculating a resultant. Suppose, for instance, that we are in a jet airliner, and our northerly velocity, v, is 387.3 knots, and our easterly velocity, u, is 216.8 knots. Then our vector diagram is like this. Although we carry out addition of two vectors, the aircraft does not travel first north, then east. What happens, of course, is that it is flying up the resultant, and the resultant of v and u is the vector of track and ground speed. The problem is solved using elementary trigonometry, finding the track from the tangent, which is given by u over v, and finding the ground speed by Pythagoras. This sort of fairly simple calculation can be performed using only calculator-level technology. There is no complex computing involved. Typically, this would be carried out several times a second and continuously refreshed on the display, so it would seem to the pilot to be continuously calculated. In this example, we have a true track of 029.3 and a ground speed of 444 knots. The velocities are also passed forward to a second stage integrator, where they are converted into distance gone, or displacement north and displacement east. These are labelled S subscript n and S subscript e in the picture. It is necessary for the initial position to be input into an INS before use, so that the system knows where it is starting from. The relationship between nautical miles and change of latitude is a simple one. 1 minute of change of latitude is 1 nautical mile, anywhere on the Earth. 1 degree of change of latitude is 60 nautical miles. So suppose that, in this example, the start position were 5137.3 north, and you had flown 20.5 nautical miles northwards. Your SN value of 20.5 minutes change of latitude would be added to the start latitude to give a present position of 5157.8 north. This means that you have a continuous readout of your present latitude, in just the same way as the tripometer on your car continuously tells you your present distance along a route. Longitude is slightly more complicated, because 1 minute of change of longitude is 1 nautical mile only at the equator. You can see that the distance on the Earth at latitude B, between the same change of longitude, is less than it is at latitude A, the equator. This east-west distance on the Earth is called departure, and is measured in nautical miles east or west. The equation linking departure and change of longitude is that change of longitude in minutes equals departure over the cosine of latitude. However, there is a mathematical function called the secant, which is simply the reciprocal of cosine. For instance, the cosine of 60 degrees is 0.5, so the secant will be 1 over 0.5, which is 2. So we can rewrite the above formula as change of longitude in minutes equals departure times secant latitude. This gives us a computing method for calculating the change of longitude. SE is coming out of the second stage east-west integrator. SE is nautical miles in the east-west sense. This is departure. We therefore take this departure and multiply by the secant of latitude. Present latitude is already available to us, so the system takes a pick-off latitude from the North Channel and feeds it to a microprocessor, which calculates the secant and multiplies it by the output of the east-west second stage integrator, thereby converting the departure into change of longitude. Let's just sum up that data flow again, because we are going to use it to build on in a future lesson. We have a north and an east accelerometer. They sense every change of aircraft movement and pass it to first stage integrators. The first stage integrators continuously add up these accelerations, thereby converting them to velocities. The velocities are used to calculate track and ground speed, and they are also passed to second stage integrators, where they are converted to distance gone. The northerly distance gone is simply added to the initial position to generate a new latitude. However, the easterly distance gone has to be converted to change of longitude. We need an input of latitude. Fortunately, we already have it. It is the current latitude part of present position in the display. The latitude therefore passes to a secant multiplier. This converts it to change of longitude, which is added to the initial position to generate a new longitude. Because of the speed at which computers operate, this process is repeated many times a second. We therefore have a continuously updated present position. Let's summarize the whole lesson now. There are various different forms of accelerometer, but the pendulous E and I bar type is a fairly common one. The actual mechanization does not need a long vertical bar, and practical accelerometers are usually a rectangular shape, with the long side horizontal. Integrators convert a rate of change over a period of time into total change over that time. It is essential that the accelerometers are mounted on a table that can rotate, pitch, and bank, called a platform, in order that they can be kept pointing north and east. The platform servos have to be rapid response and very accurate, and the platform is heavy. This is difficult to engineer. Consequently, the servos used to wear out quickly on early models of INS. Finally, we covered the data flow from the accelerometers to the display. That concludes this lesson. The next one will cover platform stabilization.
In this lesson, we're going to look at the gyroscopes on the INS platform and how they need to be corrected. However, we'll start by reminding ourselves about the data flow in INS from the last lesson. We have a north and an east accelerometer. They sense every change of aircraft movement and pass it to first stage integrators. The first stage integrators continuously add up these accelerations, thereby converting them to velocities. The velocities are used to calculate track and ground speed. And they are also passed to second stage integrators, where they are converted to distance gone. The northerly distance gone is simply added to the initial position to generate a new latitude. However, the easterly distance gone has to be converted to change of longitude. We need an input of latitude. Fortunately, we already have it. It is the current latitude part of present position in the display. The latitude is therefore passed to a secant multiplier. This converts it to change of longitude, which is added to the initial position to generate a new longitude. Because of the speed at which computers operate, this process is repeated many times a second. We therefore have a continuously updated present position. Accelerometers are quite similar in principle to a spirit level. Suppose you were to jerk a spirit level sharply to the right. The bubble would move because of the inertia of the liquid. But what would happen if the spirit level were not perfectly horizontal? The bubble would also move. How can you tell the difference? The answer is that you can't. You have no way of knowing what's causing it. Exactly the same problem applies to an accelerometer. It's designed to sense lateral accelerations when it's on the level. There is no problem because g, the gravity vector, is at 90 degrees to the sensitive axis and so is not sensed by it. However, if the accelerometer is on the tilt by an angle of, say, theta, the sensitive axis will pick up a component of gravity of g sine theta, even if the aircraft is on chocks and not going anywhere. This would be disastrous. As we said, the integrators would not know that these false accelerations were really components of gravity and would start integrating them, thereby generating false velocities. A constant acceleration would very rapidly build up into a very large velocity. Think what happens when you hold the accelerator pedal down on your car. These rapidly increasing velocities would then be passed to the second stage integrators, where they would very rapidly build up into distances gone. We would have a runaway system, all this whilst the aircraft is still on chocks. This must not be allowed to happen. The solution is to keep the accelerometers level. The accelerometers are therefore mounted on a platform, which is kept level by tying it to a gyro. In fact, there are 3 gyros, not 1. And all of them are horizontal axis gyros. We need to modify our previous diagram of data flow in order to incorporate these changes. However, in order to keep the diagram simpler, we will show only the north channel. Precisely the same modifications are necessary in the east channel, but we are not showing them in order to avoid duplication. Although there are 3 gyros and they are actually horizontal axis, we will diagrammatically show only one and we'll show it vertical axis to make it clear that its job is to keep the platform horizontal, just like an artificial horizon. The types of gyro used in INS can either be rate integrating gyros or 2 degree of freedom displacement gyros. Rate integrating gyros are widely used. The rate integrating gyroscope is a single degree of freedom gyro using viscous rather than spring restraint. However, the details of its construction need not concern us. We should simply note that, although mechanically it is a single degree of freedom system, because of the integration process, its output behaves as though it were a 2 degree of freedom system. The gyroscopes are not mechanically tied to the airframe or to gravity, and would be space gyroscopes, having no mechanism to tie them to correct for real wander. However, mathematically computed corrections for apparent wander, that is, Earth rate and transport wander, are applied. Space gyros remain orientated to a fixed point in space. But the whole purpose of INS gyros is to keep the platform level to local Earth, but without using gravity as a sensor. This means that corrections for gyro wander need to be applied. The broad subdivisions of gyro wander are into real and apparent. Real wander is caused by mechanical imperfections such as gimbal friction or rotor imbalance. Unlike apparent wander, the spin axis is actually moving with respect to space. Real wander is minimized by high-quality engineering and manufacturing techniques. These techniques are expensive, requiring special metals, jeweled bearings, liquid sealing, clean rooms with airlocks, and other high-technology methods. However, when the money is spent, real drift rates of around 1/100th of a degree per hour were typical for 1970s tuned rotor gyros. It can therefore be said that, with INS technology, real wander is so low that the gyros can almost be regarded as ideal gyros. This leaves us with apparent wander. You will remember that this is split into earth rate and transport wander. They are both needed to stabilise the platform. We need to examine earth rate in more detail to understand how INS alignment takes place, why it takes so long, and why the aircraft cannot be moved whilst it is happening. We also need to examine transport wander in more detail to understand how some types of INS errors are caused and why they have a sinusoidal waveform. These are the well-known Schuler errors. The way the earth rate varies with latitude will depend on whether it is the horizontal component or the vertical component of earth rate which is being considered. We'll start by considering the horizontal component. Imagine an aircraft parked on the equator with a gyro axis pointing to true north, that is, aligned with the local meridian. As the Earth rotates from position 1 to position 2, the gyro axis remains fixed in space and also remains aligned with the local meridian. At the equator, the gyro direction has not changed with respect to Earth direction. It is still pointing in a direction parallel to the original one, which is true north. Earth rate is therefore 0. However, in this picture we are looking down on the North Pole. The gyro and the meridian are in line. As the Earth rotates, the meridian changes its direction with respect to space, but the gyro does not. This gives us an equation for the horizontal component of Earth rate, which we have met before. It's 15 times the sine value of the latitude in degrees per hour. Now, let's look at the vertical component of Earth rate. You have to understand this in order to appreciate how alignment takes place and why it becomes difficult or impossible at high latitudes. We are looking down onto the North Pole and the aircraft is parked at the equator with the gyro running. The wings are level and the gyro axis defines the horizontal, or wings level. The Earth then rotates, taking the aircraft with it, to position 2. The gyro, being rigid in space, has retained its space orientation. The orientation of the aircraft to the gyro has changed by 90 degrees, and the gyro is now indicating 90 degrees of bank. So, at the equator, we get the full 15 degrees per hour of vertical component of Earth rate. Now the aircraft is at the North Pole, or latitude 90, and we are looking at the Earth from sideways on. As before, the wings are level, and the gyro axis defines the horizontal, or wings level. In this case, no matter what the rotation of the Earth, there will be no change in indicated bank angle. Earth rotation will give apparent yaw, but no apparent bank. So, at the pole, we get 0 degrees per hour vertical component of Earth rate. The cosine of 0, or the latitude of the equator, is 1. The cosine of 90 degrees, or the latitude of the pole, is 0. This gives us an equation for the vertical component of Earth rate. It's 15 times the cosine of the latitude in degrees per hour. Corrections for Earth rate, based on the sine and cosine of the latitude, therefore need to be computed and passed back to the platform in order to keep it level as the Earth rotates. Fortunately, latitude is being constantly updated in the North Channel. All we have to do is constantly feed the latitude to a computer which continuously calculates 15 degrees times sine latitude and 15 degrees times cosine latitude per hour, and pass it to the appropriate channel of the platform. As with Earth rate, there are two components of transport wander, horizontal and vertical. Let's start with horizontal. We've seen this before. Although transport wander takes place at the same time as Earth rate, we shall explain them separately for simplicity. So, disregarding Earth rate for a moment, imagine the Earth stopped in space, not rotating. We have an aircraft at Los Angeles with its gyro aligned with north up the local meridian. This is the solid white line. The aircraft flies from Los Angeles to London. When the aircraft arrives in London, the gyro is still aligned with the same direction in space, the dotted white line. However, the actual direction of true north from London is the line connecting London to the North Pole. The difference is the horizontal component of transport wander, which is in fact the difference in the alignment of the meridians at Los Angeles and London. Horizontal transport wander is actually meridian convergence. There is an equation which we have met before. The horizontal component of transport wander is u over 60 times tangent of latitude. Again, we can continuously calculate this correction by computing. We already have u in the east channel and a continuously updated latitude in the north channel. So, similarly to the way we did before, we can feed a continuously changing value of u and another continuously changing value of latitude to a computer, which continuously calculates u over 60 times tangent latitude and passes it to the appropriate channel of the platform. So, we're now onto the correction for vertical component of transport wander. This is also known as Schuler tuning. It has nothing to do with Earth spin. It is because, as we travel over the Earth, the gyro would remain fixed in space. But the local direction of the horizontal changes. Our accelerometers are affected by gravity, and they must be kept horizontal to local gravity. The traditional way of keeping gyros and instruments level is by using gravity, for instance, by using mercury gravity switches. But as we've pointed out before, the accelerometers themselves would be the best choice for gravity sensors. However, they are being used for sensing horizontal acceleration. Like the spirit level, you can't use the same device to give you both gravity and accelerations. It's one or the other. So we continue to use the accelerometers to measure horizontal accelerations, and we have to find another way to keep the platform at right angles to the gravity vector. As you might expect by now, a mathematical method is used. Here's a picture of an aircraft at the equator, along with the local horizon at the equator and the radius of the Earth. The aircraft now flies, say, 60 nautical miles northwards. The horizon has changed. Knowing the distance d and the Earth's radius, we can work out the angle theta, which is the amount of change of horizon. It would be tangent of theta equals d over r. If you do the sums, it comes to exactly 1 degree. This is what you would expect from a change of 60 nautical miles directly northwards. However, in reality, it would not be sensible to wait till the aircraft had flown a distance before feeding in a correction to the gyro. The gyro attitude should be adjusted as soon as the aircraft starts to travel. Therefore, instead of using d, the distance gone in the above equation, we take v, the velocity, northwards and use it to find omega, the angular velocity. Omega is the rate at which we need to correct the platform. It will be a value in degrees per hour. The equation now becomes omega equals v over r. We know r, the radius of the Earth. Its average value is 3,437.7 nautical miles. To find omega, we need v, but we already have it. It is coming out of the first stage north-south integrator. All we have to do is take a parallel value out of this source and divide it by r, then feed it back to the gyro, like this. There are, in fact, 2 feedback loops, one in the north channel the V over R loop, which keeps the platform level as the aircraft flies around the Earth northwards or southwards. There is also a U over R loop in the east channel to keep the platform level as the aircraft flies around the Earth eastwards or westwards. Schuler tuning is, in fact, an electromechanical velocity feedback loop, as shown here. The purpose is to keep the platform level with the local horizon as the aircraft travels around the Earth. However, some people find it helpful to imagine a huge pendulum with a length equal to the Earth's radius, with the platform bolted on at right angles. The bob of the pendulum remains at the centre of the Earth. Then, as the aircraft travels, the circular motion of the rigid part of the pendulum keeps the platform level. This pendulum analogy is more helpful when considering the nature of Schuler errors, which we will come on to in a future lesson. Let's look at the full list of platform corrections now. Some have been met before, but 2 of them will be new. These 2 don't need to be understood in such detail. Firstly, there is the correction for aircraft manoeuvres. You'll remember that the platform has to be kept north orientated, level in pitch, and in roll. Next is earth rate. The sine and cosine of latitude are continuously computed and fed back to the platform. There is transport wander. The horizontal component is corrected by continuously computing U over 60 tan latitude and feeding it back to the platform. And the vertical component is corrected by the V over R and the U over R feedback loops, otherwise known as Schuler tuning. The first of our new ones is Coriolis. Here's a simple explanation. You're flying down a meridian towards the equator in the northern hemisphere. Your direction with respect to Earth is due south. But the Earth is rotating. So your track with respect to space is curved. If you're flying a curved path in space, there must be an acceleration into the centre of the curve. This can be calculated and allowed for. And finally, there is central acceleration. Again, a very simple explanation. Imagine yourself flying around the Earth. If you really were travelling in a straight line, you'd disappear off into space. Clearly, that doesn't happen. There must be a force accelerating you into the centre of the Earth. Again, that has to be calculated and allowed for. So, to summarise, the full list of platform corrections is aircraft manoeuvres, earth rate, transport wander, Coriolis, and central acceleration. Now that we see the need for Schuler tuning, we can look at the full data flow, including the V over R feedback loop. The accelerometer is mounted on a platform which is stabilised and north orientated by gyroscopes. It detects accelerations which are passed to the first stage integrator. Here they are integrated into velocity. One feed of this velocity is taken forward to the second stage integrator, where it is converted to distance gone and added to the present position, thereby generating a new present position. A parallel feed of the velocity is fed backwards through a V over R feedback loop, where it is converted to the omega term which is used to rotate the gyro to keep the platform perpendicular to the local gravity vector. The same sequence is taking place simultaneously in the east channel, the only difference being the addition of a secant multiplier to convert SE into change of longitude. There have been very few new ideas in this lesson, We have met most of them before. What makes this lesson important is the way they interact. So we'll summarise what we've covered. Firstly, we revised the basic data flow without Schuler tuning. Then we saw that, like spirit levels, accelerometers can't distinguish between being accelerated horizontally and being tilted. We therefore have to mount the accelerometers onto a platform and keep it horizontal to the gravity vector by using gyros. Modern, expensive manufacturing techniques have made real wonder so low that the gyros can be regarded as almost perfect. However, that still leaves apparent wonder. Earth rate is corrected by calculating the sine and cosine of latitude and using them to precess the gyros. The horizontal component of transport wander, or meridian convergence, is also corrected by calculation. The vertical component is corrected by V over R and U over R feedback loops, which is also known as Schuler tuning. Some people find the pendulum analogy helpful when considering Schuler tuning. We looked at the full list of platform corrections. And finally, we revised the full data flow, including Schuler tuning. We are not going to add anything more to this diagram. For our purposes, this is as complicated as it gets. However, we do need to consider how we initially set the system up by levelling it and getting it to point north before we start taxiing. This process is called alignment, and we will cover it in the next lesson. All of our previous description of the theory behind inertial navigation systems assumes that the system is up and running. The platform is levelled and north-orientated. It is therefore necessary to initialize the platform before flight in order to get it level and orientated. This process is called alignment. Details of the various stages of alignment vary from manufacturer to manufacturer, with some using stages known as course levelling, course alignment, fine levelling, and fine alignment. However, all systems share the same three broad stages. These are caging, levelling, and gyrocompassing. The gyros used in INS spin at about 25,000 revolutions per minute, and some designs are quite heavy. Usually, we need a powerful motor to spin them. However, at startup they are static and so have no rigidity. The gimbals and gyros could be in any position. It simply depends on where they stopped when the gyro ran down after its last use. If we suddenly start these powerful motors without parking the gyro in a safe configuration, we could damage the gyro or gimbals. The inner gimbal is therefore driven to a position at 90 degrees to the outer gimbal, and the outer gimbal is driven at 90 degrees to the frame. This is called caging. We can now run the motor up. Additionally, to give good stability and accuracy, the gyro needs to be run at a constant operating temperature within a narrow band of limits. Once it is up and running, we need a ventilation system to get rid of the waste heat. However, in order to get the system at temperature quickly, we apply heater voltages initially. This whole process takes about 3 minutes and is fully automatically controlled by the computer. Once it is complete, alignment proceeds to the next stage, which is levelling. It is absolutely essential that the gyros are as level as possible before we start. You remember that we said that accelerometers can be compared to spirit levels. You can either use them to measure horizontal accelerations or to establish the horizontal, but not both at the same time. However, during the alignment process, we don't need to measure horizontal accelerations. The aircraft is on chocks. It isn't going anywhere. The accelerometer output should be 0 for a stationary aircraft, but if the platform is tilted, it senses a component of gravity along its sensitive axis, During levelling, these outputs, instead of being integrated into velocities, are passed directly back to the levelling motor, which tilts the gyro and platform back until zero acceleration is sensed. At this point, the platform is levelled to the local gravity vertical. Levelling also takes about 3 minutes. The system now automatically proceeds to the next stage, which is gyro compassing. Gyro compassing is the process of rotating the platform so that it takes up an orientation of true north. Gyro compassing senses the heading with reference to the Earth's spin axis, which is true east. Note that Earth magnetism is not used. It depends on the principle that an ideal gyro, being space-referenced, can detect Earth rate. In the high-quality gyros used in INS, the real wander is so low that they can be considered as ideal gyros. This picture shows that if the gyro axis is pointing east at the equator, the gyro will be sensitive to Earth rate. Whilst this one shows that if the gyro axis is pointing north, there is no Earth rate at the equator. This horizontal component is, as we showed earlier, 15 times the cosine of latitude in degrees per hour. At the equator, we get the full 15 degrees per hour when pointing east, and 15 times the sine of the latitude in degrees per hour when pointing north. This is 0. At any other latitude, we get intermediate amounts, depending on the latitude. As gyro compassing starts, the platform has been levelled like this. But as the Earth rotates, the platform initially stays rigid in space. The aircraft, which is still on chocks, stays with the Earth. This will cause the accelerometers to detect gravity. The platform is therefore rotated by servos until the accelerometers stop detecting gravity. This means that the gyro axis must be pointing north. This is taken as the reference heading for the INS. Gyro compassing takes about 11 minutes at medium latitudes. So, with approximately 3 minutes for caging, 3 minutes for levelling and 11 minutes for gyro compassing, the entire alignment process normally takes about 17 minutes, though it does vary with latitude. The INS needs to know starting latitude in order to calculate the correct Earth rate, using 15 times the sine and cosine of latitude degrees per hour. If the latitude inserted at startup is wrong, the alignment will be incorrectly computed. In fact, if the latitude error is considerable, the INS may not align at all. Examiners sometimes set questions using a figure of 10 degrees of error as the limit. Note, however, that longitude is not used in the alignment calculations. If an incorrect longitude is inserted at startup, there will be a present position error, but it will not affect the accuracy of the alignment. Therefore, we can say that INS alignment is sensitive to incorrect latitude, but insensitive to incorrect longitude. We now come on to why it was necessary for you to understand that the vertical component of Earth rate depends on the cosine of latitude. It is the cosine of latitude that determines the amount of Earth rate which we can use for gyro compassing. Cosine is a function that gets smaller as latitude increases. This means that the accelerometers are trying to detect smaller and smaller amounts of Earth rate as latitude increases. Thus, an alignment at high latitudes takes longer than one at low latitudes and is slightly less accurate. However, at very high latitudes, the amount of Earth rate is so small that it is swamped by the error tolerance of the accelerometers, and alignment is not possible at all. This occurs at around 70 to 75 degrees north or south, depending on the vintage of the INS. If ground alignment can be achieved at a lower latitude, the aircraft can be subsequently operated at high latitudes, but it cannot be initially aligned at high latitudes. We said earlier that, if you move accelerometers sideways, you can't use them for measuring the vertical. Therefore, the aircraft cannot be moved at all during the alignment process. The slightest movement off chocks will destroy the alignment and you will have to start again. With many aircraft, it is not possible to align with engines running. Even gusty wind conditions can prevent alignment. Alignment is completed when the Ready Nav light comes on. The MSU selector can then be moved from Align to Nav, and the aircraft can be subsequently moved without damaging the alignment. Let's summarize this lesson. Alignment takes place in 3 stages: caging, leveling, and gyro compassing. Caging the gimbals protects the gyros whilst they are being spun up. The gyros are also warmed up. It takes about 3 minutes. The system then automatically proceeds to the leveling phase. The accelerometers are used as gravity detectors, and the platform is erected to the local horizontal. This also takes about 3 minutes. Gyro compassing is the process of rotating the platform so that it takes up an orientation of true north. Gyro compassing senses the heading with reference to the Earth's spin axis, which is true east. It takes about 11 minutes at medium latitudes. So, with approximately 3 minutes for caging, 3 minutes for leveling, and 11 minutes for gyro compassing, the entire alignment process normally takes about 17 minutes, though it does vary with latitude. It is essential that the correct initial latitude is entered. However, an incorrect initial longitude does not degrade alignment. Alignment is limited to latitudes of less than 70 degrees or so. If this is achieved, the aircraft can be subsequently operated at high latitudes, but it cannot be initially aligned at high latitudes. The aircraft cannot be moved at all during the alignment process. Even the vibration from a running engine or gusty wind may prevent alignment. This concludes the initial lessons on IN theory. We shall return to it later when we consider IN errors, but the next lesson looks at practical operation of the equipment. This lesson describes the operation of typical 70s-era inertial navigation systems such as the Litton LTN-51 and the Delco carousel. Before any INS operation can take place, both AC and DC power supplies must be available from the aircraft buzz bars. These may be initially provided from an external power unit or the APU. Eventually, the power must be provided by internal aircraft power from the alternators or generators. The INS Mode Selector Unit, or MSU, is then switched from off to standby. This allows aircraft power through to the INS and initiates the IN's own power supplies. With standby selected, it is now possible to enter an initial present position. Switch the MSU rotary switch to POS, which stands for Present Position. Note that the keypad has some multifunction keys. For instance, 2 is also N, which stands for North. 4 is also West. 6 is also East. And 8 is also South. In present position mode, the keypad will accept only N or S as the first key press. It will not misinterpret them as 2 or 8. Enter the present position using the format N or S, followed by degrees, degrees, minutes, minutes, decimal minutes. At the first key press, that is N or S, the insert blue light comes on. It is both a button and a light. Now put in the latitude. Check the entry in the light emitting diode or LED display. If the entry is incorrect, use the Clear button to correct it, one space at a time. Now enter the longitude. This will be E, or W, followed by degrees, 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 minutes, minutes, decimal minutes. Again, the system will accept only E or W for the next press. It will not misinterpret them as a 6 or a 4. There are only 5 digits for the latitude because the maximum number of digits for the degrees is 2, as you can't have more than 90 degrees north or south. However, there are 6 digits for the longitude because 3 digits are needed for the degrees as there are up to 180 degrees of longitude. Once satisfied that the present position that you have entered is correct, press the Insert button. The Insert light goes out and the present position is entered into the computer. Alignment can now begin. Select the MSU rotary switch to align. Alignment may take up to 17 minutes and the countdown starts when the switch is set to align. Alignment is then under automatic control by the computer and no further aircrew actions are required until it is complete. On completion, the MSU green Ready Nav light will come on. After this, the crew will switch the rotary selector to Nav when ready to move. Alignment can also take place with Nav selected on the MSU rotary switch. If, after inserting present position in standby, a double click through Align to Nav is made, the internal computer will put the system into align mode despite the switch position until alignment is complete. At this point, the Ready Nav light will come on and the system will automatically go into nav mode without any further selection. Clearly, it is advisable to select Align or Nav as early as possible in the checklist sequence, as there will be 17 minutes to wait before the aircraft can be moved, and it would be better to do the bulk of the pre-start checks after selecting Align in order to make productive use of the time. It is possible to check on how much time remains to complete the alignment, although there is not much point. It will not make the alignment any faster. However, the facility exists during alignment by use of the desired track system status position on the CDU rotary switch. There are 2 windows on the CDU LED display, left and right. In POS and waypoint, the left is for latitude and the right for longitude. In any other mode, the left is for the first named and the right for the second. In desired track system status, the desired track will not be applicable at this stage because no waypoints will have been selected, but during alignment, STS gives an indication of time remaining to complete the alignment. The detail of the display varies from manufacturer to manufacturer. In some systems, the display is minutes to go to completion of alignment, and on others there is a code number that gives an indication of which substage of alignment is currently taking place. In the Lytton system, for instance, 40 indicates fine align. This gives an approximate estimate of time to go. However, the most useful way to spend the time waiting for alignment to complete would be to load the waypoints. This can be done before selecting Nav. Up to 9 waypoints can be stored at any one time. To select which store to load, there is a small thumb wheel. Rotate the wheel to the appropriate store. Then select the rotary display switch to WPT. The method of entering a waypoint is exactly as for entering a present position. Repeat this procedure for the first 9 waypoints of the route. If there are more than 9 on the route, subsequent waypoints can be loaded in flight once the early ones have been overflown and are no longer required. Once alignment is complete, select Nav. The alignment is now protected and the aircraft can be taxied or pushed back. If the system operates normally, it will now remain in Nav until final shutdown. Although the INS will provide heading, track, ground speed and drift for general navigation, One of its most useful facilities is waypoint steering. A flight plan route of initially up to 9 waypoints can be entered, and a steer signal to follow the route along its various legs can be generated and displayed on the flight director system, either as a guide or to the autopilot to automatically steer the aircraft along the route. The INS is not always connected to the autopilot, and therefore it is possible for the aircraft to be positioned off its desired INS track. To enter a waypoint steer, press the Track Change button. The blue lights in the Track Change button and also the Insert button light up. Then enter the pair of waypoints to steer between in the order from to. In other words, to steer from waypoint 1 to waypoint 2, enter 1, 2. The numbers 1, 2 appear in the LEDs above the Track Change button. Press the Insert button to enter them into the computer. The Track Change and Insert lights go out. If the Auto Manual Remote Selector is switched to Auto, then, on reaching waypoint 2, an automatic changeover takes place. The LED display changes to 2, 3, and the aircraft is steered along the next leg. It is normal when route flying to use auto mode and automatically change over from leg to leg. Almost all routes will require more than 9 waypoints. This is no problem. Suppose waypoints 1 and 2 have been overflown and the aircraft is now on the leg between waypoint 3 and waypoint 4. Waypoints 1 and 2 are no longer required. Waypoint 10 can be loaded into store number 1 and waypoint 11 can be loaded into store number 2. As the aircraft completes the leg from waypoint 8 to waypoint 9, the automatic changeover will go to 9, 1 for the next leg. So, provided that the waypoint stores are updated in flight by the crew when the previous waypoints are no longer needed, it is possible to run through the 9 waypoint stores as many times as is required. The alert light warns the crew of the approach of a waypoint. Otherwise, the aircraft could roll to 25 degrees of bank at waypoint changeover onto the new heading without the crew expecting it, which could cause concern on the flight deck. The exact indications vary with the model of INS and the mode selected, but in most systems the alert light gives a steady illumination at about 2 minutes to go, changing to a flashing light at 30 seconds to go. The steer signal tracks the aircraft down the centre line of the route between the 2 waypoints in use. If the aircraft is out to the side of the route for any reason, it will be S-turned back onto the centre line at quite a sharp angle. It is not steered directly to the next waypoint. However, there is a facility for steering directly from present position to a waypoint. This is called waypoint 0. It is not possible to preload a waypoint 0 because there is no 0 selection on the thumb wheel. But if the operator selects Track Change 0, 2, Insert, the present position at the moment of pressing Insert is inserted as waypoint 0, and the aircraft is steered from that position directly to waypoint 2. The various displays available on the control and display unit are selected by use of the rotary selector switch. With the rotary selector on track and ground speed, the left display shows the true track to the nearest 1/10 of a degree, and the ground speed to the nearest knot. Selection of heading and drift angle gives a left display of true heading to the nearest 1/10 of a degree, and a right display of drift expressed as degrees left or right, also to the nearest 1/10 of a degree. For cross-track displacement and track angle error to be operative, a steer between 2 waypoints must be selected. The left display shows the cross-track displacement from the centre line between the 2 waypoints. It would look like this. The diagram shows a desired track of 060 degrees. The aircraft is positioned 12 nautical miles to the right of the desired centre line. The right shows the difference between the aircraft track at the present time and the desired track between the waypoints in use. This would look like this. The aircraft's actual track at this time, which is the instantaneous combination of heading and drift, is 20 degrees left of the desired track between the selected waypoints. With the rotary switch at POS, the present position latitude is shown in the left window, and the longitude in the right window. Both are shown to an accuracy of the nearest 1/10 of a minute of latitude or longitude. Selection of waypoint displays the latitude and longitude of whichever waypoint has been selected in the waypoint selector thumb wheel to the nearest 1/10 of a minute of latitude or longitude. With the rotary selector in distance to go and time to go, the left-hand display shows the distance to go to the nearest nautical mile, and the time to go to the nearest 1/10 of a minute from present position to the 2 waypoints along the route, between the 2 waypoints selected in the From To LED display. The time to go is calculated from the present ground speed, and the system is responsive to changes in ground speed. If the thrust is reduced, as the speed trickles off, the operator can see the time to go increasing as he watches. With wind selected, the left window shows the wind direction to the nearest degree, and the right one shows the wind speed to the nearest knot. In order to calculate wind velocity, 4 inputs are required. These are heading, drift or track, ground speed, and true airspeed. The INS generates the first 3 itself. It is necessary to have an input of TAS from another source in order to calculate wind velocity. On its own, INS has no facility for calculating TAS. However, any aircraft which has an avionics suite sophisticated enough to include an INS will also include an air data computer which will provide the TAS to the IN. DSR Track STS stands for Desired Track and System Status. The desired track is the initial Great Circle true track between the waypoints selected in the From To LED display, and is shown to the nearest 1/10 of a degree. We mentioned earlier that system status can give an indication of time remaining to align. However, once NAV has been selected on the MSU rotary switch, STS is used to indicate serviceability and for fault diagnosis. If the INS is serviceable, a code, usually 0000, appears in the right-hand LED. Its main use, however, is for fault diagnosis in conjunction with the red WARN light. The INS carries out a continuous process of self-monitoring as part of its operating routine. If any malfunction is detected, the WARN light illuminates. The WARN light simply indicates that there is a failure. It does not tell the operator what it is. To diagnose the fault, select Desired Track, System Status. In the right-hand window, a 4-digit status code will be indicated. This 4-digit group is used in conjunction with the pilot's operating handbook. In the malfunctions checklist, there is a table consisting of 3 columns. The first gives the numerical code, the second identifies the failure, and the third gives the appropriate action to be taken. Finally, the test function is used for deeper diagnosis by the maintenance personnel and is not normally used by flight crew. Selection of test causes all the lights to light up and puts an 8 in every LED, since 8 is the one number that uses every element of the 7-line display. This can be a useful function if you suspect that an LED in a number display is faulty. For instance, a 7 can appear as a 1 if one LED element has failed. On pressing the Hold button with the rotary selector in POS, the LEDs freeze and the Hold button lights up. On pressing the hold button a second time, the light goes out and the display unfreezes to the new present position. Whilst the hold light is on, it is only the display which is frozen. The internal calculation of present position continues. We'll now look at the yellow CDU battery light. It is essential that electrical power to the INS is not lost, even briefly, during flight. If it were, computing would stop and alignment would be lost. As we have already discussed, it is not possible to align in flight. The aircraft must be stationary on the ground. Therefore, in the event of INS power failure, all computing and navigation facilities will be lost until the end of the flight. This must not be allowed to happen, and so the INS contains its own battery, which is constantly charged from the aircraft power supplies. In the event of an aircraft mains power failure, the battery simply takes over, and power supplies to the INS are maintained. This is indicated by illumination of the CDU BAT light. The battery will last for a reasonable period of about 20 to 30 minutes, during which time the crew should attempt to reconnect aircraft main power. There will be a fault-finding checklist, which will vary from aircraft to aircraft, usually along the lines of check the circuit breakers, then check the fuses, then try resetting failed alternators, generators and inverters, and finally try switching to an alternative buzz bar. If any of these succeed in returning the aircraft main power, the CDU BAT light goes out. The situation is recovered, the battery is recharged, and no harm has been done. Otherwise, the MSU red battery light will shortly appear. There is also an MSU red battery light. As we said, the battery has only a limited charge. If the voltage drops below a specified level with time, the INS functions can no longer be preserved. In this case, the MSU battery light illuminates. This is more serious. It means that the battery is the sole source of power to the INS, and that the battery is failing. When the battery power drops below a predetermined level, alignment is lost and, in time, all INS facilities will be lost. Even if power is subsequently restored, it will not be possible to realign and all navigation computing functions remain lost. We now come on to the attitude reference function. There may be occasions when full navigation computing is not available, but the gyros are serviceable. This could be in the event of a computing malfunction so that earth rate and transport wander corrections cannot be calculated, or it could be after an alignment failure in flight. On many aircraft, the gyros are used as primary attitude information, as well as for inertial navigation, and it may be possible to retain gyro information. This is done by selecting ATREF on the MSU, which disconnects the computing and loses alignment if this has not already happened anyway. The accelerometers now act as gravity switches, as they do during the levelling phase of alignment, and the gyros become gravity tied in the long term. They become Earth gyros. The system now gives attitude information and a limited form of heading. The gyros are normally very accurate, but there is no correction for earth rate and transport wander, and the heading needs to be reset periodically to an independent source, which is usually a magnetic compass. In effect, the gyros are acting as a super-accurate form of DGI and as an attitude indicator. That completes the lesson on INS operation, so we'll summarise what we've covered. Selection of standby on the mode selector unit connects aircraft power to the IN. It also allows present position to be entered. Moving the MSU to align starts the alignment process, which continues automatically for approximately 17 minutes, depending on the latitude. On completion, the MSU Ready Nav light will come on. However, it is also possible to align with the MSU selected to nav. Once alignment is complete, we select Navigate. The alignment is now protected and the aircraft can be taxied or pushed back. If the system operates normally, it will now remain in nav until final shutdown. Attitude reference, or ATREF, as the position is labelled, is used only in the event of a computing malfunction or loss of alignment. It maintains the operation of the gyros, but all computing and alignment is lost. It gives attitude and a limited form of heading. We then looked at the control and display unit and went through each of the rotary switch functions. The alert light gives warning of approaching waypoint changeovers. The warn light is used to indicate malfunctions. And the CDU battery light tells us that we have lost aircraft power to the IN and that the IN's own internal battery has taken over. However, if the MSU battery light comes on, we have lost INS alignment and computing for the rest of this flight. Waypoint 0 gives us the facility to steer directly to a waypoint from present position instead of a longer route. And the Hold button freezes and unfreezes the present position display. We also mentioned that the INS needs an input of true airspeed if it is to have the facility to compute wind velocity. Now that we know something about INS theory and also practical operation, we can go on to look at errors in the next lesson.
This lesson is on inertial navigation system errors. Firstly, we need to remind ourselves how the information flows in the INS in order to work out what the sources of error will be. The accelerometer is mounted on a platform which is stabilized and north-orientated by gyroscopes. It detects accelerations, which are passed to the first stage integrator. Here they are integrated into velocity. One feed of this velocity is taken forward to the second stage integrator, where it is converted to distance gone and added to the present position, thereby generating a new present position. A parallel feed of the velocity is fed backwards through a V/R feedback loop, where it is converted to the omega term, which is used to rotate the gyro to keep the platform perpendicular to the local gravity vector. The same sequence is taking place simultaneously in the east channel, the only difference being the addition of a secant multiplier to convert the easterly distance gone, or SE, into change of longitude. So, where are the possible sources of error? There are 6. We'll explain them in more detail in a moment, but first we'll list them. These errors are platform tilt, accelerometer bias, integrator error, leveling gyro topple, initial azimuth misalignment, and azimuth gyro drift. Let's start at the beginning. Firstly, the platform may not be perfectly level. Platform tilt can also be known as initial leveling misalignment. The leveling process during alignment is very accurate. Ideally, it should be within about 6 seconds of arc. This is 1/600th of a degree. Nevertheless, it is a compromise with the requirement for a reasonably short alignment time. On completion of the alignment, the platform may not be perfectly level. Accelerometer bias is next. The accelerometers are designed to give 0 output for 0 input, if properly levelled. However, due to manufacturing imperfections, there may be some slight output when the accelerometer is perfectly stationary and level. This is called accelerometer bias. Next, we'll look at integrator error. For a 0 input into an integrator, there should be a 0 change of output. Again, due to manufacturing imperfections, there may be some slight scaling error. Taking the second stage integrator as an example, suppose the velocity input were exactly 400 knots for exactly 1 hour. If the distance gone output to the present position display were 401 nautical miles instead of 400, that would be an integrator scaling error. Integrator error can be present in both the first stage and the second stage integrators. The next error to consider is leveling gyro topple. We said that the platform and gyro might not be initially perfectly level. However, the gyro may also topple from its start position. With the accuracy to be expected of IN quality gyros, the topple rate would be of the order of only 1/100th of a degree per hour. But nevertheless it is finite and would have an effect on the output. Apart from leveling, there is also the heading output to consider. Horizontal direction is called azimuth, so this error is called initial azimuth misalignment. Gyro compassing usually results in an initial alignment accuracy of about 0.1 of a degree. This is very accurate compared with a gyromagnetic flux valve heading, but even 1/10 of a degree introduces appreciable errors. Finally, there is azimuth gyro drift. In addition to any initial misalignment error, the azimuth or heading gyro may also drift. This drift rate would typically be of the order of only 1/100th of a degree per hour. But as with the topple, it is finite and would have an effect on the output. So this comes to 6 input errors, or 7 if we split the integrator error into first stage and second stage integrators. We are now going to see what effect they have on the output data. The first error we're going to look at is platform tilt. But before we do, we need to modify our diagram slightly. We shall want to see what effect these errors have on acceleration, velocity and position. The basic pattern is unchanged. We still have an accelerometer on a platform. The output is acceleration, but this time we've put an imaginary meter in so that we can see what's happening to the acceleration. With the needle at the 12 o'clock position, that means no output. If it is over to the left, that means a positive acceleration. If it is over to the right, it means that there is a negative acceleration. The acceleration goes to a first stage integrator, where it becomes velocity. The velocity goes onwards to the second stage integrator. But again, we can monitor it with our next imaginary meter. And again, vertical means 0 output, left means positive, and right means negative. Here's the second stage integrator, with its output of distance, for which we used the same convention. It's just easier in this diagram to see a needle presentation than changing digits for latitude and longitude. Finally, there's the V/R feedback loop. And here is the gyro. So now let's see what effect is caused by an initial leveling misalignment or platform tilt. Imagine that we are on the ground, alignment has just completed, and we switch the MSU to navigate mode. Here's the basic diagram. But unfortunately, on completion of the alignment, there is some leveling error. The component of gravity will be misinterpreted as a false acceleration. So let's show this false acceleration on our meter. This acceleration will be passed to the first stage integrator, where it will be integrated into velocity, and then to the second stage integrator, so that it will be integrated into change of position. At the same time, the velocity is passed back along the V/R feedback loop. The system can't tell that we are still on chocks, and this is a false velocity, so it assumes that the aircraft is travelling around the curvature of the Earth, and slowly brings the platform to the level, which means that the source of the false acceleration is removed. You might think that this has solved the problem. The platform is now level, and there is no false acceleration. However, it hasn't. We have a build-up of velocity. The way that an integrator works is that if you have 0 acceleration going in, it doesn't mean that you have 0 velocity going out. It means that you have zero change of velocity. Therefore, the velocity continues to be passed to the second stage integrator and to the position display, displacing the position further. And it also continues to be passed back along the V/R loop, thereby rotating the platform as far over in the opposite sense as it was at the start. So the acceleration is now negative. This will become a negative velocity, which will be integrated to reduce the distance error and fed back to bring the platform back to the level. However, we still haven't finished. We still have a velocity in the system, which will be fed back to drive the platform to its original position. So the system is now in precisely the same configuration as it was at the moment of selecting Navigate. The whole loop has oscillated one full cycle to return to its initial configuration. It will continue to oscillate in this manner until the INS is switched off. We have had an apparent change of position and then a return to the original position, even though the aircraft has not actually moved. This type of periodic error pattern is called a Schuler oscillation. This is the Schuler pattern of error caused by platform tilt. It is sinusoidal in form. 2 cycles of oscillation are shown in this picture, but in practice the oscillation will continue until the INS is shut down at the end of the day. The distance error starts at 0 at the moment of selecting Navigate, then increases to half of its full displacement after a quarter of a cycle, reaches its fullest displacement at the halfway point of the cycle, then reduces back to half displacement at 3/4 of the way through, and finally reduces to 0 at the end of the cycle. Each cycle takes 84.4 minutes. This never changes, because it is based on the constants in the V/R feedback loop. These are the value of gravity and the radius of the Earth. Therefore, it does not matter whether your INS was designed by Honeywell, Delco, Lytton, or anyone else. It will have to have a V/R feedback loop to keep the platform level as it travels over the Earth. And if the platform is not level at the start, there will always be an oscillation with a period of 84.4 minutes. This is called the Schuler period. The maximum value of the Schuler error does not increase with time. Whatever the amplitude of the first cycle, all subsequent cycles will have the same amplitude. The oscillation is self-sustaining because the system is resonating at its natural frequency. Most people find the explanation of Schuler errors using the moving diagram a little complicated, and you are not expected to be able to remember it in detail. This is why the pendulum analogy is popular. When we discussed platform stabilization in an earlier lesson, we said that the V/R feedback loop could be likened to a large pendulum with a length equal to the Earth's radius, with the platform bolted on at right angles. The bob of the pendulum remains at the centre of the Earth. Then, as the aircraft travels, the circular motion of the rigid part of the pendulum keeps the platform level. Continuing with this analogy to explain Schuler's errors, if the platform is not level at the start, then this is like starting with the pendulum off-centre. When the pendulum is released, it will swing with a period of 84.4 minutes. As the aircraft travels round the Earth, the Schuler loop will still try to keep the platform levelled with the local horizontal, which is what it's designed to do, but it will have an unwanted Schuler oscillation superimposed onto it. Let's now see which of our errors will give a Schuler pattern. Firstly, we'll remind ourselves of the full list. Then we'll look at the feedback loop to see what caused the platform tilt oscillation error. The problem was caused by a feedback of false velocity through the V/R loop. So if any of the input errors gives us a false velocity, we will get a Schuler oscillation. Let's look at what could cause a velocity error. As we have seen, the platform might not be level. Secondly, there might be an accelerometer bias. And finally, there might be first stage integrator error. These are the only three. The combination of contributions from all three gives us our Schuler error. These errors are also known as bounded errors because they do not increase with time. We'll now go on to unbounded errors. There are other errors and they do not follow this sinusoidal pattern. Instead, they get worse with time. The second stage integrator is a good example. It is outside the V/R feedback loop. Suppose an aircraft were to fly at exactly 400 knots for an hour. But the second stage integrator were to output 401 nautical miles distance gone. Then, after 2 hours, the aircraft would have actually flown 800 nautical miles. But the integrator would have output 802. After 3 hours, the true distance is 1200 nautical miles. But the integrator would have output 1203, and so on. This kind of error is a different pattern. It is called a ramp or unbounded error. Another obvious example of an unbounded error is initial azimuth misalignment. Clearly, the further you go, the worse the cross-track error gets. There are 4 sources of unbounded error, and they combine to form a ramp pattern. In practice, Schuler errors and ramp errors occur at the same time. So we have a ramp pattern like this, with a Schuler ripple superimposed on top of it, so that the complete error pattern looks like this. Here is a summary of INS errors. Bounded errors oscillate about a mean value and have a sinusoidal form with a period of 84.4 minutes. They do not increase with time. They consist of platform tilt, accelerometer bias, and first stage integrator error. Unbounded errors increase with time. Their form is a ramp. They consist of initial heading misalignment, leveling gyro topple, azimuth gyro drift, and second stage integrator error. Unlike our earlier diagrams, which were idealized, this is an actual plot of INS against GPS on a test flight. The pattern can be clearly seen. There is a basic ramp increasing at approximately 1 nautical mile per hour, with a 1 mile Schuler oscillation superimposed on it. How can we correct or remove these errors? The answer is that we can't. All of these bounded and unbounded errors result from limitations in the accuracy of the components of the INS. They arise from the accelerometers, the integrators, and the gyros. They can all be considered to be a more sophisticated form of instrument error. There is nothing that can be done about them within the INS itself, except to improve engineering standards. And this did happen with the evolution of better and better manufacturing techniques during the 70s and 80s. Even with these errors, the general accuracy of an INS is good compared with previous systems. This plot shows only an 8-mile error after 9 hours of flight. For a standalone system, this is very good. However, from the 90s onwards, 2 developments occurred. One was the introduction of the ring laser gyro to replace the old tune rotor gyros. Systems using these new gyros were usually called inertial reference systems. We shall cover the ring laser gyro and the IRS in more detail in the next lessons. The other was the idea of using the INS or IRS as only one component of a multi-sensor system, and to have a method of extracting the most probable position from a combination of all of the inputs. This multi-sensor system is part of the Flight Management System, or FMS for short. And the method of establishing the most probable position from a variety of inputs is called Kalman filtering. The later generation of inertial systems, which are generally known as Inertial Reference Systems, or IRS, are usually part of an Integrated Flight Management System, FMS. In the Flight Management Computer, or FMC, there are usually 2 or 3 IRSs, each generating its own present position. These IRS positions are compared with independent sources, such as Global Positioning System or GPS, and computer-generated calculation of cross-cut positions, which have been obtained from ground-based radio beacons called distance measuring equipment. The computer automatically selects those DME stations along the route which will give the best crosscut, and calculates an independent new position several times a minute. The crosscut positions are called DME positions. Not all inputs are always available. DME is a line-of-sight system, so it can be blocked by hills or the curvature of the Earth. GPS can have blank spots. A process known as Kalman filtering produces a statistically most probable position known as the FMC position. From this FMC statistical best estimator position, it is possible for the FMC to establish an error trend over a period of time, and to build mathematical models of both the Schuler and the unbounded error propagation pattern. This is then used in the computation of future computer-generated positions. Kalman filtering is complicated and does not lend itself to broad simplifications. However, it is important to realize that the FMC position is not the average of the IRS and DME or GPS position, but is computer-generated using a sophisticated statistical algorithm. Let's summarize this lesson. We reminded ourselves of the basic data flow diagram. Then we identified the sources of error. We looked at sources of error within the V over R loop. And we saw why Schuler oscillations happen. We reminded ourselves of the pendulum analogy for normal platform stabilization, and then extended it to include the platform not being level at the start. The Schuler period is always 84.4 minutes. And the maximum displacement at the successive 42.2 minute points is always the same. We then said that there were other errors that don't fit this pattern, and that these are known as unbounded errors. This is the summary of errors, which you must remember. They give an error propagation pattern like this. On a standalone INS, these errors cannot be removed. They can be minimized by the use of more accurate components and expensive engineering techniques. However, the later generations of inertial systems are only one of several sources of position in a flight management system. And a statistically most probable position is computer-generated by the Kalman filter in the FMS. However, the FMC position is not the average. This concludes our study of INS. The next lesson goes to look at its successor, the IRS.
This lesson is the first of 3 on the Inertial Reference System, or IRS. Between approximately 1970 and 1990, the Inertial Navigation System, which we studied in previous lessons, continuously evolved and developed. Instead of having a single standalone system with its own present position display, it became normal to have 2 or even 3 inertial sensors which passed their outputs to a central computer. Each of these inertial sensors is called an inertial reference system, and its outputs go to the flight management computer. The term inertial reference system, as opposed to inertial navigation system, is usually used if the reference datum is a ring laser gyro instead of a spinning disc type of tuned rotor gyro. We'll look at how a ring laser gyro works shortly. There are three main characteristics which define what we now call an IRS, which make it recognisably different from a first-generation standalone INS. These are greater system integration, use of ring laser gyros, and much greater computer power. We'll look at each one of these in turn to see what has changed over the last 20 to 30 years. The primary sources of information in the IRS are 3 ring laser gyros and 3 inertial accelerometers. Notice that we have 3 channels this time: forwards, sideways, and down. This is in contrast to most INSs, which had only 2. The system needs to know initial present position. Unlike INS, it does remember where it was shut down at the end of the last flight, but nevertheless, this needs to be refined by a fresh input of present position from the pilot. It also needs barometric altitude. As we just said, there is a vertical accelerometer and a vertical channel. However, on its own, the vertical channel is too unstable. The vertical accelerometer picks up the instantaneous changes, but the barometric information stabilizes the vertical velocity and altitude outputs. Other than that, all we need is TAS from the air data computer. As with the INS, TAS is needed in order to be able to compute wind velocity. Let's look at the outputs of an IRS and see how they compare with the traditional INS. This is an inertial reference unit. It provides the outputs for the aircraft's avionics. Firstly, it gives primary pitch and roll attitude. That was also provided by the INS. It gives both true and magnetic heading. We're already familiar with the idea that inertial systems operate in true because they align themselves by detecting Earth spin. The INS gave us true heading. However, whilst the IRS navigation and computing is all carried out in true, normal aviation practice is to use magnetic directions for all air traffic control instructions and airways information. Pilots therefore need to know their magnetic heading. The IRS, being more modern than the INS, has a greater computer memory. This allows it to have a database of latitudes and longitudes throughout the world, and the magnetic variation associated with each point. But variation changes rapidly near the magnetic poles, and the information becomes unreliable. The calculation of magnetic heading is therefore limited to latitudes of, typically between 73 degrees north and 60 degrees south. Above these latitudes, only true heading is available. Acceleration is measured in the longitudinal, lateral and normal sense, in other words, forwards, sideways and down. Note that, unlike INS, we now need 3 accelerometers, not 2. Also, notice that the horizontal accelerometers are not north and east this time. They are longitudinal and lateral. The IRS gives angular rates of pitch, roll and yaw, just as the INS did. And it gives inertial velocities north-south, east-west and ground speed, as the INS did. However, it also gives baroinertial vertical rate. The IRS gives latitude and longitude position information, as the INS did. But it also gives a baroinertial altitude. It gives wind speed, wind direction and drift, as the INS did. From this raw data, it calculates various items of secondary data which are used in the flight management system and the electronic flight instrumentation system, both of which we will cover later. Looking at the full list The biggest changes to notice are the vertical channel and the availability of magnetic heading. In our introduction, we said that the first characteristic of an IRS, which makes it recognisably different from a first-generation standalone INS, is greater system integration. Integration is a word with at least two different meanings. Up till now, we have used it in its mathematical context in integral calculus to mean the opposite of differentiation. However, we will now use it in a more general, non-mathematical way to mean a system with many components which are interactive and interdependent. In the 1960s, aircraft were not generally designed as integrated systems. For instance, a large airliner would have been primarily conceived in terms of airframe and engines. Usually, instruments were thought about afterwards and were not normally specific to the type. Off-the-shelf items would have been used. The INS would certainly not have been designed in at the outset and might well have been retrofitted as part of a mid-life update. Nowadays, by contrast, an aircraft is practically a flying computer. Many of them are actually unstable or even uncontrollable in the event of a total computer failure. At the outset of a design of an aircraft, such as the Airbus 380, the chief avionics systems designer would have been a very important member of the project team. Modern aircraft are designed from the outset with the IRS as a central data source for many other systems. Inertial information is used in the flight management computer, the flight control computer, the thrust management computer, and the stability augmentation system. If you have studied the yaw damper, you will know that traditional yaw dampers have their own rate gyro. However, this is no longer necessary if the information is available from the IRS. Traditional weather radars also have their own gyroscope in order to keep the scanner horizontal as the aircraft banks. Otherwise, during the bank, the picture would be degraded as one side would be too bright, and the other side would be blank as the energy went out into space, never to return. Therefore, the scanner must be kept stable with a gyro. But instead of having a dedicated scanner gyro, these days the reference comes from the IRS. Ground speed is fed to the anti-skid auto brake systems, and attitude information is used in the attitude director indicator, and navigation information in the horizontal situation indicator. The vertical speed indicator is rate aided from the vertical accelerometer. This is sometimes called an inertial lead unit. And all attitude, acceleration, velocity and position information is, of course, continuously fed to the flight data recorder. Let's summarize what we've covered so far. There are three main characteristics which make an IRS recognizably different from a first-generation standalone INS. These are greater system integration, the use of ring laser gyros, and much greater computer power. The outputs of the IRS are broadly similar to those of the older INS, but with the addition of a vertical channel and a magnetic database. Modern aircraft are designed with the IRS at the heart of an integrated avionics system, which avoids duplication of sensors such as auxiliary gyros and other less accurate data sources. The next lesson will go on to consider the ring laser gyro. This lesson is the second of three on the Inertial Reference System, or IRS. In the last one, we said that there were three main characteristics which define what we now call an IRS, which make it recognizably different from a first-generation standalone INS. These were greater system integration, the use of ring laser gyros, and much greater computer power. We'll now go on to consider the second of these, the ring laser gyro. The biggest single change of technology in IRS is the use of non-rotating gyros. INS used tuned rotor gyros, that is, spinning discs, which are the same type as all the other gyros you have studied until now. By contrast, IRS uses ring laser gyros, which have no moving parts. Over the last 40 years, it has become possible to miniaturize lasers down to a size small enough to use in aircraft. Look at the pattern of the laser light, which is shown in yellow here. This is a picture of an IRS inertial reference unit. It is mounted in the aircraft with this end facing the front. You can recognize that laser light pattern. Two of the laser gyros are easy to see. Here is the gyro which measures pitch. This one measures yaw. But you can also see a little spot of light here. This is the third gyro, set at right angles to both the other two. This one measures roll. These ring laser gyros are not gimbaled. They are fixed to the airframe, and they change their orientation as the aircraft maneuvers. The accelerometers are also in fixed positions, longitudinal, lateral, and normal or vertical with respect to the airframe. A system where the gyros and accelerometers are fixed to the airframe and maneuver with it is called a strap-down system. This is in contrast to INS, which was a gimbaled system. The ring laser gyro measures angular rotation. Unlike previous methods, there is no system of comparing a gyro with gimbals in order to measure an angle. It is a completely new principle to us, and it depends on a property of light known as the Sagnac effect. Suppose that we have a circular tube and that we can send light round it in both directions. If the tube is stationary and we start both beams at the same time, they will arrive at the same time. However, if the tube rotates during the passage of the light beam travelling in the same direction as the end point in the tube takes longer to arrive, and the one travelling in the opposite direction takes a shorter time. We can measure this difference in light path and use it to detect rotation. In practice, it is difficult to make light travel on a circular path, but the same effect is achieved using straight light paths reflected by mirrors into a triangular pattern. Also, in practice, when dealing with the speed of light, it is not possible to measure such small differences in time. We can, however, measure a frequency shift between the two beams. The ring laser gyro utilizes the Sagnac effect. It is basically a triangular glass prism containing drilled tubular cavities. This is a cathode. Its function is to emit photons, which are minute particles of light. There are two anodes, which are of opposite electrical polarity to the cathode. A large potential difference is maintained between the cathode and both anodes, which causes the photons to be powerfully attracted towards the anodes. The potential difference between the cathode and each of the anodes is the same, and so the photons are equally attracted to both. The light therefore divides, approximately half of it travelling clockwise and half anti-clockwise. The drilled tubular cavities are filled with a helium and neon gas mixture. This acts as a conducting medium, and so the light is channeled down these specific paths. One of the defining characteristics of lasers is that they produce what is known as coherent light, that is, light at a single frequency. Normal light, such as sunlight or light from an electric bulb, is usually known as white light, but it actually contains all the colours of the visible spectrum, which are all at different frequencies. Laser light is not like this. It is one colour only, usually a kind of pinkish orange, and each beam has only one frequency. The continuous circulation of the light in each direction has an amplifying action which builds up to a saturation point. At this point, standing waves form. When this happens, it is called lasing. This lasing can only occur if there is a whole number of wavelengths in the path distance. This determines the laser light frequency, which will be the same for both the clockwise and the anti-clockwise light in a stationary prism. However, if the prism rotates about its sensitive axis, the number of wavelengths in each path length remains the same, but the path lengths change. This means that the frequencies must change. Conversion of the frequency change into a measure of angular rotation rate is achieved by use of interference pattern technology, which is explained in the next scene. Interferometry is a measurement technique used in various scientific applications, such as X-ray crystallography and radio astronomy. An interference pattern is formed whenever two beams of light or any other form of wave motion converge on a single point. Let's start by explaining it with water. Imagine that a brick is dropped into a pond. Circular waves of ripples will radiate out from where the brick went in. As seen from sideways on, the waves will look like this. A cork in the water would stay in the same place laterally, but would bob up and down as the waves pass through it. There will be peaks and troughs. As seen from above, it will look like this. Now imagine that two bricks are dropped into the pond simultaneously. The wave pattern will look like this. Here are the peaks and troughs. Now imagine that this is light, not water. Where two peaks meet, there is a build-up of intensity, and in between, it is darker. Now let the light fall onto a screen. We get a pattern like this. With two light sources at the same frequency and phase, the pattern remains static. But if the frequencies alter, the pattern moves. The direction and rate of pattern movement are a measure of the aircraft's rotation direction and rate. The laser gyro contains a photoelectric detector. It can tell if the interference pattern is static, and, if it is moving, it can detect the direction and rate of rotation. One problem associated with the ring laser gyro is called laser lock. The two laser beams can synchronize and, if this happens, they give zero output even when the aircraft is altering its attitude. A piezoelectric dither motor therefore provides a constant input of vibration at a known frequency, which prevents laser lock. The same signal also has to be sent to the computer to tell it to ignore the introduced vibration and simply measure the difference between the dither motor input and the laser gyro output, which is the desired measure of angular rotation. Let's sum up this second lesson on inertial reference systems. We said that the biggest single change which makes an IRS different from an INS is the use of ring laser gyros. These ring laser gyros are not gimbaled. They are fixed to the airframe and they change their orientation as the aircraft maneuvers. This is known as a strap-down system. Ring laser gyros measure the Sagnac effect to establish angular rotation rate in pitch, roll and yaw. Lasers produce coherent, that is, single frequency light. If the prism rotates, the number of wavelengths in each path length remains the same, but the path lengths change. This means that the frequencies must change. The two light sources arrive on a screen where an interference pattern is generated. With two light sources at the same frequency and phase, the pattern remains static. But if the frequencies alter, the pattern moves. The direction and rate of pattern movement are a measure of the aircraft's rotation direction and rate. Ring laser gyros suffer from laser lock, but the problem is avoided by use of a piezoelectric dither motor. That concludes this lesson on the ring laser gyro. The next one looks at how the angular rotation rate information is referenced to the horizontal and to direction on the Earth. This lesson is the last of 3 on the Inertial Reference System, or IRS. Previously, we said that there were 3 main characteristics which define what we now call an IRS, which make it recognisably different from a first-generation standalone INS. These were greater system integration, the use of ring laser gyros, and much greater computer power. This lesson looks at how that greater computing power is used to relate our measurement axes to the horizontal and to directions on the Earth. The lesson also brings together points from all 3 IRS lessons. The laser gyro can measure our aircraft's changes of orientation very accurately, but we still need a reference datum for our basic directions: longitudinal, lateral, and normal. We do not have a stable platform with IRS. Our accelerometers are pointing in the direction of the airframe. However, for our velocities to be useful to us, we need them in terms of north, east, and vertical. This situation is resolved by making use of the great increase in computer power which has become available in the last 30 years. We can construct a mathematical model to solve the problem. The technique is called axis transformation. Imagine our aircraft in some particular flight attitude. And here is some point in 3-dimensional space which we wish to define. It can be defined by the coordinates x1, y1 and z1. Now imagine that the aircraft pitches, rolls, and yaws. The point in space has not moved, but the reference axes have. It is now defined by a new set of coordinates, x2, y2, and z2. The mathematics of converting from one frame of reference to another is called axis transformation. The advent of powerful rapid computers makes it possible to carry out these transforms so quickly and frequently that the system is effectively working in real time. The computer makes use of the technique of matrix algebra, which handles these many complex equations very rapidly. With our computer, we no longer need a platform. We can have the gyros and accelerometers attached to the airframe and manoeuvring with it. The task of the platform servos in the older INS is now carried out by algebraic matrix transformation in the IRS. One of the weaknesses of the INS platform servos was the failure rate resulting from their mechanical complexity. With the IRS, however, there is very little to go wrong. We simply have light passing through glass and microvoltages in an integrated circuit. Consequently, failures are extremely rare. This is often expressed as the IRS having a longer life cycle. In the maintenance world, this is called the mean time between failures, or MTBF, and it is costed. Ring laser gyros are subject to the same laws of gyrodynamics as the older tuned rotor gyros, and therefore need to have the same corrections applied to them. As we said in an earlier lesson, these are Earth rate, transport wander, Coriolis, and central acceleration. The equations for all of these are known, and therefore mathematical calculation of them has been built into the computer model, along with the corrections for aircraft manoeuvres. The correction for the vertical component of transport wander means that the mathematical model is Euler-tuned, and even though it is nothing more than a series of equations, it has exactly the same effect on the attitude output as the older form of mechanical Euler tuning. We therefore have the same problem that, if the initial horizontal datum is not exactly level, we will get Euler errors. The use of a mathematical model does not avoid the errors associated with INS. we simply model them in the computer. The axis transformation system needs to establish the horizontal level and the direction of true north, just as the platform in INS did. Here is an INS-equipped aircraft with a platform parked on sloping ground. Here is its longitudinal axis. During the levelling phase of alignment, the platform and the accelerometer mounted on it would be driven down to the horizontal. With IRS, the accelerometer stays in its fixed position, but the axis transformation system can establish the angle between the accelerometer's axis and the horizontal. The computer remembers this and uses it as the initial datum. The same process is carried out for the initial lateral levelling error. Once the system has been correctly levelled and earth rate corrections for the correct latitude applied, any remaining error can only come from incorrect alignment with true north. By analysing the residual forces, the computer's axis transformation system can establish the direction of the Earth's spin and therefore find true north. This process of finding the difference between the longitudinal, lateral and normal axes and the directions of north, east and vertical is sometimes referred to as establishing the trihedron. The whole process is simply the IRS equivalent of levelling and aligning the platform in INS. A trihedron is the meeting point of three planes at right angles to each other. We are now going to compile a list of the main differences between INS and IRS. We have mentioned most of these before during this series of 3 lessons, but some will be new. INS gyro drift is low because of the high-quality engineering used in its manufacture. What there is comes from gimbal friction and mass imbalance. The gyro drift from IRS is even lower. It arises from laser noise caused by imperfect silvering of the mirrors. INS accuracy is generally good. Position error growth rates of 1 to 2 nautical miles per hour are typical. IRS accuracy is better. It is difficult to put a figure on it because the output is invariably fed into a flight management system and processed further, but the raw IRS position error growth rate is probably about half a mile an hour or better. IRS suffers from the specific problem of laser lock, which the INS does not have. However, the lock is overcome by the incorporation of the piezoelectric dither motor. There are 3 rate integrating gyros in INS, and they are mounted on a stabilized platform. The IRS has 3 strapped-down ring laser gyros. There are 2 accelerometers in INS mounted on a gyro-stabilized platform, which keeps them pointing north and east. The IRS has 3 strapped-down accelerometers, fixed in the longitudinal, lateral and normal planes. The horizontal and vertical datums in INS are maintained by a gyro-stabilized platform. Whilst in IRS, this is achieved by algebraic matrix transformation in a mathematical model. Accelerations are integrated into velocities and velocities into distances in both INS and IRS. There is a difference in the way that INS and IRS deal with gravity. In INS, it is assumed to be 1g everywhere. The superior memory capacity of IRS allows us to have a database which stores small differences in the local value of gravity. In both INS and IRS, the gyros are fundamentally space gyros, and therefore corrections for Earth rate and transport wander have to be computed and applied. However, this is achieved by platform torquing in the INS and algebraic matrix transformation in the IRS. Schuler tuning is used in both systems, and therefore Schuler errors occur in both. Alignment in INS is carried out by means of gyrocompassing, that is, sensing the direction of east from Earth rate and then torquing the platform until no further Earth rate can be detected. The platform must then be pointing north. Alignment by gyrocompassing also takes place in IRS, but by algebraic matrix transformation. It is alternatively known as establishing the trihedron. When entering initial position prior to alignment of INS, it is essential that the latitude is as correct as possible. Any error will degrade the accuracy of the alignment. However, longitude is not used, and longitude error does not affect alignment accuracy. By contrast, IRS has a non-volatile memory. It remembers its last position prior to the previous shutdown. If there is any significant difference between that last position and the new position entered by the pilot on startup, either in latitude or longitude, an error message is generated. A correct latitude and longitude are both required for alignment to commence. The alignment time for INS is about 17 minutes at temperate and low latitudes. About 3 minutes of this is caging, 3 minutes is levelling, and gyrocompassing takes about 11 minutes. IRS aligns more rapidly. About 10 minutes at temperate and low latitudes is normal. One of the reasons for the shorter alignment of IRS is that mechanical caging of tuned rotor gyros during startup takes about 3 minutes. No caging is required for the ring laser gyro, and typically the lasers fire up in less than a second. The construction of the INS platform servos is mechanically complex. They therefore had a shorter mean time between failures. The laser gyros used in IRS are mechanically simpler and highly reliable. Consequently, they have a longer life cycle. Tuned rotor gyros have mass and experience gimbal friction. Consequently, they are sensitive to aircraft maneuvers and G forces. Maneuvering and G have little or no effect on the accuracy of ring laser gyros. Dynamic range means that the system is sensitive and accurate when dealing with both small and large accelerations. The IRS sensors perform better at both ends of the scale. Let's summarize the main points from this lesson. There is no gyro-stabilized platform in IRS. Instead, the gyros and accelerometers are fixed to the longitudinal, lateral and normal axes of the aircraft, and they maneuver with it. This is known as a strap-down system. Conversion of longitudinal, lateral and normal axes of the aircraft into the directions of north, east and earth vertical is carried out by a process of mathematical modelling known as axis transformation. Ring laser gyros are subject to the normal laws of gyrodynamics and therefore need to be corrected for Earth rate and transport wonder. Use of a strap-down system does not avoid the errors associated with INS. We then compiled a list of the similarities and differences between IN and IRS, showing that, in general, IRS is a more accurate, more robust and more reliable system. That concludes these lessons on IRS. Later lessons will go on to show how the IRS is used in the flight management system. This is the first of 2 lessons on the flight management system, which is often abbreviated to FMS. This one is mainly on components and hardware, whilst the second concentrates on equipment operation. All modern airliners contain a flight management system. It combines various subsystems into one integrated system, designed to provide continuous automatic navigation, guidance and performance management. FMSs can vary considerably from manufacturer to manufacturer and type to type. The system architectures can be different and different manufacturers often use different names for the same basic components. This makes it difficult to generalize about them, and the details of any particular system will be studied during your type conversion. However, they all contain the following basic subsystems. A Flight Management Computer, or FMC. This is the central processor which combines all the other components into an integrated system. It also carries out the navigation, guidance and performance calculations. A Control and Display Unit, or CDU, for each pilot. This allows them to input information through a keypad and receive information through a display screen. Our arrows therefore go both ways. 2 or possibly 3 inertial reference systems to provide position, altitude, acceleration and velocity information to the flight management computer. An Air Data Computer, or ADC, to give altitude and airspeed information. There are radio navigation inputs, navigation and performance databases in order to provide route, navigation aids and basic aircraft data, and engine and fuel data. The pilots manage this system in order to generate commands to the flight guidance system. This is a generic term which can either mean the flight director display on the electronic flight instrument system, or can mean the autopilot. This is the layout of an early model of the FMS fitted to the Boeing 737-400, and although it did not have GPS, it was very similar to our basic model. You can see that there is one flight management computer serving both pilots and 2 inertial reference systems. However, here is a later model. The architecture looks more complicated because there are 2 flight management computers, 1 for each pilot, and 3 inertial reference systems. However, the basic components are the same, and the way the system works is the same. The commands generated to the flight guidance system give 2 types of guidance. The first is lateral navigation, or LNAV. This is in the horizontal plane, steering the aircraft left or right as required to follow a route through a series of waypoints to the destination. The second is vertical navigation, or VNAV. This is the vertical profile and takes account of the optimum flight level for the weight and distance, the fuel used, and the diversion requirements. FMS lateral navigation is more comprehensive than the simple waypoint-to-waypoint navigation provided by a first-generation inertial navigation system. The greater computer power available in more modern systems allows a lateral flight plan to include the following: the takeoff runway, including an update of present position on takeoff, the standard instrument departure, or SID, the transition from the end of the SID to the en route flight level, waypoint steering en route, the transition from the top of descent to commencing the standard instrument arrival, the standard instrument arrival, or STAR, the selected instrument approach to the landing runway, a missed approach and go-around, if required, and a flight plan to an alternate airport. Vertical navigation is also complex, and there is a lot of interaction with lateral navigation. We will show some of these facilities by the use of examples. For instance, here is a section of a takeoff and climb profile. If there is a noise abatement procedure at an airport, an aircraft will be required to climb quickly to minimize noise at low level. To achieve this, the climb is carried out at takeoff safety speed plus 10 knots until past a specified waypoint. We will then assume that there is an air traffic control requirement to maintain 250 knots indicated airspeed until reaching 10,000 feet. We need to cross a radio facility called Alpha Bravo Charlie above 4,000 feet. The computer will have to compute whether, with our present thrust, our airspeed of 250 knots will give us the required rate of climb. Next, we must cross Bravo Charlie Delta at 6,000 feet. Above 10,000 feet, we continue with the climb at the aircraft's economical climb speed, which will vary with the weight and static air temperature, and which will be calculated by the computer and passed to the auto throttle. A climb power setting which reduces the N1 by 3% is often used in order to save engine wear. We will assume that, at this weight, this setting gives a climb speed of 302 knots IAS, converting to 0.597 Mach. This is the point at which the Mach number becomes more limiting than the IAS. At the top of the climb, the aircraft is commanded to level flight and is accelerated to the economical cruise speed. Again, this is calculated by the computer, taking into account weight, altitude, and temperature. As the aircraft proceeds along the level portion of the route, as fuel is burnt and the weight reduces and as the temperature changes, the optimum economical cruise speed is continuously updated. There may come a point along the route where the aircraft is now light enough to make it worthwhile continuing the cruise at a higher flight level, subject to air traffic constraints. This is called a step climb. The considerations for the descent are similar. A top of descent point is computed automatically. Speed, distance, and altitude constraints require continuous calculation of required thrust right down to the final approach. A high-speed descent or a fuel economy descent may be selected. We'll now look at some of the components. The first of these is the Control and Display Unit, or CDU. This is the piece of equipment that allows the pilots to communicate with the FMC. It consists of a plasma display and a keypad. Let's start with the display. You can see that, about 3/4 of the way down, there is a horizontal dotted line. Above the line, we have the fields. These are specifically for data entry and are used in connection with the line select keys. Below the line, we have the scratch pad. As the name suggests, it is where we make draft entries and check them before we commit them into the computer. Suppose that we want to enter a gross weight of 61,700 kilograms at startup. We type in 61.7. We can now check it, and if there is a mistake, clear it and re-enter it. When we are satisfied that it is correct, we touch the line select key. The number jumps from the scratch pad to the field. However, the scratch pad also has a second use. The computer is programmed to pass relevant information to the pilot should it be necessary. These are called alert or advisory messages. Alert messages have the highest priority and they identify a condition which must be acknowledged and corrected by the crew before further FMC guided flight is advisable or even possible in some cases. Advisory messages have lower priority and inform the crew of the CDU entry errors or system status. Below the display is the keypad. There are number keys, letter keys, and function and mode keys to select particular pages or functions. There are also 4 indicator lights called annunciators. The first is the display light. The CDU is menu-driven and there are many different pages available. If the page that the crew have selected is not related to the active flight plan leg or the current operational performance mode, the display light reminds the crew that they are not using the optimum page. The fail light illuminates if any FMC failure is detected. The generation of any alert or advisory message causes the message light to illuminate. This will then draw the crew's attention to the scratch pad. Finally, there is a function in the FMS called offset. The aircraft can be programmed to fly parallel to, but a fixed distance from, the FMS programmed track. This could be used to avoid the turbulent wake of the aircraft ahead, for instance, or to increase separation from opposite direction traffic. Unfortunately, the display on the electronic flight instrument system does not make it obvious that the offset is being flown, so the offset light stays on to act as a reminder. The CDUs are used during pre-flight to manually initialize the IRS and FMC with dispatch information, flight plan routing, zero fuel weight, and planned cruise altitude. In flight, they are used to control the FMC and display flight information, and to show alert and advisory messages. There are two databases, one for navigation information and the other for performance information. The navigation database contains the position and, where required, the elevation and frequency of navigation aids, airports and runways. It also contains the operator's route structure, airways, waypoints, SIDs, stars and approach procedures. This information is subject to constant update, so the period of validity of any set of data is 28 days only. A new set is issued by the company supplying the data and is loaded into the flight management computer, usually from a form of compact disk. This can only be done by the maintenance personnel. Pilots cannot access the permanent navigation database. Two sets of navigation data must be carried, one for the current 28-day period and one for the following one. The 28-day period of validity is called an AIRAC cycle. Unless two sets of AIRAC cycle data are present and one of them is current, the FMS will not continue with its startup sequence. There are also two other navigation databases, the supplemental and the temporary. If the pilots need to use some information not in the permanent database, such as unpublished waypoint, they can insert it into the supplemental or temporary nav database through the CDU. Supplemental data is stored indefinitely unless removed by the crew. The temporary nav database is erased automatically on shutdown. There is also a performance database. This contains information on climb and cruise performance, thrust limits, maximum and minimum altitudes for various configurations, drag characteristics, and expected fuel flow. Maintenance personnel can refine this data by entry of correction factors for individual aircraft's drag and fuel flow characteristics, which are established from the aircraft's history. We said earlier that an FMS may be structured to have either one flight management computer or two. On those systems that have two, there are reversionary modes. Here is the system in its normal configuration. This is called dual mode. Each flight management computer produces independent calculations. The outputs are compared and checked for agreement. Minor differences are synchronized to one nominated FMC, usually the captain's. This results in both pilots' CDU displays being identical. However, if the cross-check shows a discrepancy above a predetermined value, the system changes to independent mode. This happens automatically in some systems and is selected by the crew in others. The synchronizing link between the two systems is broken. Now we have independent calculation and independent output. The pilot's displays may now conflict, and, if they do, it is up to the crew to choose which is the most likely to be correct. Finally, we may get a failure of one computer. In this case, the remaining one takes over both displays. This is called single mode. It is specifically a failure mode in which one FMC feeds both displays. Both pilots' displays will be identical. Let's summarize this lesson. The flight management system is designed to provide continuous automatic navigation, guidance and performance management. They vary from type to type, but they all contain a flight management computer, a control and display unit, 2 or possibly 3 inertial reference systems, an air data computer, radio navigation inputs, navigation and performance databases, and inputs of engine and fuel data. They simultaneously compute lateral navigation, or LNAV, and vertical navigation, or VNAV. The control and display units, or CDUs, consist of a display and a keypad, and are used during pre-flight to manually initialize the IRS and FMC with dispatch information, flight plan routing, zero fuel weight, and planned cruise altitude. In flight, they are used to control the FMC and display flight information, and to show alert and advisory messages. The navigation database consists of 2 AIRAC cycles. Unless at least one is current, the system will not function. The pilots cannot alter the permanent nav database. However, they can enter information into the supplemental and temporary memories. The performance database consists of climb, cruise and descent speeds, power setting and fuel flows. On systems where there are 2 FMCs, the normal operating mode is called dual mode. If there is a mismatch of information, the system reverts to independent mode. And if one FMC fails, the remaining computer feeds both displays in single mode. That completes this lesson. The next one will deal with equipment operation. This is the second of 2 lessons on the Flight Management System, or FMS. The previous lesson covered components and hardware, whilst this one concentrates on equipment operation. There are about 30 or 40 pages available in the CDU display, depending on the model. Once the system has been initialized, these pages can be accessed either by the function and mode keys on the keypad, or by the line select keys available on the previous page. In this example, taken from one of the climb pages, the page allows you to select maximum rate of climb, maximum angle of climb, one engine out climb, or required time of arrival. However, the startup sequence always follows the same 4 pages, which are the identification page, the position initialization page, the route page, and the performance initialization page. You are not required to know how to use the CDU in this kind of detail for the exam, but we'll go through these pages to give you practical examples of how the pilot interacts with the FMC through the CDU. This is the ident page. The pilot should check that the aircraft model and engine rating in the FMC corresponds to the actual aircraft being flown. This may seem too basic to be necessary, but you should remember that all the Boeing FMCs have a strong family resemblance. It is possible for them to be put in the wrong aircraft or wrongly programmed, especially if the airline operates a mixed fleet. The same applies to the family of Airbus FMCs. Next, the start and finish periods of the nav database AIRAC cycle should be checked. In fact, if they are out of date, an alert message will be displayed. If the operational program and the latest software update are known, they can be checked too. On conclusion, the POS init line select key is pressed to move on to the next page. This is the position initialization page. The IRS has a non-volatile memory, and so will remember its last position before the previous shutdown. This is shown here. The airport, which is Amsterdam, or Echo Hotel Alpha Mike in this case, will also be remembered. The airport reference datum will be shown. If it is not already present or needs to be changed, the pilot can overwrite it. The latitude and longitude is held in the NAV database and does not need to be entered. Similarly, it is sufficient to enter the parking bay, gate Delta 16 in this example, for the latitude and longitude to appear. The pilot accepts or re-enters the initial position to commence IRS alignment. It is possible to select different time zones on many systems, but usually unnecessary. All flying operations are conducted in Coordinated Universal Time, which, for all practical purposes, is the same as GMT. Local times are not generally used in aviation. On conclusion, the Route line select key is pressed to move on to the next page. The route page starts with the departure and destination airports. In this example, they are Amsterdam Schiphol and Liverpool John Lennon Airport. It is usually sufficient to simply enter the company route number. In this example, flight number 602 is the company's route from Amsterdam to Liverpool. And it is a repetitive flight plan. The pilots should know which runway is in use by the time they program the FMC. If the company route is not already programmed, the route can be entered using the VIA and TO columns. This page offers us only one option: performance initialization. Here is the performance initialization page. The gross weight in metric tons in this example is taken from the dispatcher's trim sheet. The desired cruise altitudes are entered. The planned fuel from the trim sheet is entered. This is compared with the actual fuel gauge measurement, which is directly connected to the FMS. If there is a discrepancy larger than a specified limit, a warning will be given. The zero fuel weight is entered. This is added to the fuel figure. The answer should be the gross weight. If it is not, again, a warning is given. The forecast wind, ISA deviation and static air temperature are entered to allow the FMS to plan an estimated flight time and fuel burn. In flight, as actual data is gathered, these estimates will be continuously modified. The cost index is entered. This figure modifies the target cruising speed in order to balance the fuel costs and maintenance costs of the flight in the most economical way. This will be explained shortly. As before, there is only one page we can go to. The N1 limit can be set to reduce engine wear in the climb. Let's explain cost index. We'll use a worked example. Suppose we have an aircraft that can be flown at either high-speed cruise or long-range cruise. Let's say that over a particular route, high-speed cruise takes 3 hours and long-range cruise takes 3 hours and 10 minutes, but uses less fuel. Your job as an airline pilot is to operate the aircraft for your company as economically as possible. Which do you choose? You might think that the answer is obvious. You would select long-range cruise. But it's not as simple as that. There are other operating costs. Let's now suppose that the aircraft has to go in for planned maintenance every 1,000 hours, and it is then out of service for a week. In that time, not only is the airline paying for maintenance, but the aircraft is out of action, not generating revenue. These figures, by the way, are simply illustrations. They are not necessarily based on any particular aircraft. Let's say that if we fly at high-speed cruise, we can make 300 revenue-earning flights between maintenance. We'll allow 100 hours for positioning flights and crew training. However, if we fly to save fuel, each flight is longer and we can only get 284 revenue-earning flights in the same maintenance interval. This is a difference of 16 flights, each of which might have 100 passengers on board. We have lost up to 1,600 fares between maintenance intervals in order to save some fuel. Is it worth it? The answer is that it depends on the relative cost of fuel and cost of maintenance over the route that the aircraft is operating, and these will be different in different parts of the world. However, for each route, they can be calculated by the operator's cost accountants. There will be an optimum point which, for any particular route, is the most economical speed to fly. Cost index attempts to quantify this. It is determined by dividing aircraft operating costs by fuel costs. Only those portions of operating costs affected by trip time are included in the calculation. The range of values is then put on a sliding scale, which is from 0 to 200 for the Boeing Classic series of FMCs. If 0 is selected, the FMC gives maximum range airspeed and minimum trip fuel with a low speed descent. If 200 is selected, the FMC gives VMO or MMO for climb and cruise and a high speed descent. The company will specify a cost index to be used for each route. A required time of arrival mode is available in order to arrive on time at some designated waypoint, such as the final approach fix, holding fix, or airport. The FMC computes a recommended takeoff time, then gives target speeds to fly and continuously adjusts them in flight. Speeds are automatically corrected for in-flight winds and route changes by adjusting the cost index. If RTA mode is used, taking off late will add to the cost, as the aircraft will have to fly faster. There are occasions when the crew may be required to navigate to a waypoint that is not already stored in the permanent navigation database, for instance, following an air traffic control instruction. In this case, it is possible to create a new waypoint. This can be in one of 4 formats. The first is the simplest, latitude and longitude. Next is called place bearing and distance. For instance, Sierra Alpha Mike 180/45 means 45 nautical miles range on the 180 magnetic radial from Southampton VOR. There is also place bearing/place bearing. Sierra Alpha Mike 122/Delta Victor Romeo 218 is where the 122 Southampton radial crosses the 218 Dover radial. Note, however, that there is no place distance/place distance facility, as this would result in 2 possible solutions, and the FMC would not know which one to take. Finally, there are along track waypoints. If the route, for example, is a direct track between Southampton and Dover, then Sierra Alpha Mike 030 means 30 nautical miles along the route after Southampton, and Delta Victor Romeo -030 means 30 nautical miles before Dover. But there is no across-track facility as, again, this is not unique. It could be anywhere along the displaced track, and so is not allowable. These created waypoints are normally put into the temporary nav database and are therefore automatically erased at the end of the flight. As we said earlier, the IRS initial position is inserted using the position initialization page at startup. From this point on, there are no further updates directly to the IRS. However, the FMC position is updated. The first of these updates comes at the start of the takeoff roll. The FMC navigation database contains the position of all runways thresholds in the company's route structure. As the takeoff roll is commenced, the throttles are advanced. A contact on the throttle quadrant is called the takeoff go-around switch, or TOGA switch for short. Operation of the switch automatically updates the FMC position to the takeoff threshold. It is also possible to input a displaced threshold. Suppose that we do not need to use the whole runway length and have decided to take off from 2,300 feet past the threshold. In this case, the pilot inputs a correction factor for the displacement distance, and the new position is automatically calculated by the computer as part of the update. We are now going to look at some typical alert and advisory messages. On most systems, there are around 40 to 50 messages, and they vary in detail from system to system, so you are not required to learn these by heart. This is just to show you some representative ones and to show you how the pilots and the FMC interact. You'll remember that alert messages have the highest priority, and they identify a condition which must be acknowledged and corrected by the crew before further FMC guided flight is advisable, or even possible in some cases. Advisory messages have lower priority and inform the crew of CDU entry errors or system status. Here is a typical alert message. Thrust required. It means that VNAV is engaged. We are past the computed top of descent, and additional thrust is required to maintain the required descent path and speed. Here is another. Runway not applicable for SID. It means that the runway which the pilot has selected is not compatible with the required standard instrument departure. Details of runways and SIDs are stored in the navigation database, and it can pick up these types of mismatch. Similarly, we have the alert message, runway ILS frequency error. The FMS knows which instrument landing system frequency is associated with each runway. If the wrong one is selected, it will pick it up. Another possible message is unable cruise altitude. This is because the journey is too short for the requested cruise altitude. Suppose the route distance is 210 nautical miles and we select flight level 350. The computer will calculate the distance required for the climb to that level, taking into account weight, EASA deviation and wind. A typical figure would be 105 nautical miles. It also calculates the descent distance, taking into account the same factors. Typically, this might be 110 miles. However, the computer works on a minimum acceptable cruise time of 1 minute, which is usually about 7 miles. This would give us a minimum trip distance of 222 miles. We would therefore get an unable cruise altitude message. If we then select a lower altitude, it should work. By contrast, we have the advisory message, max altitude, flight level 390. This is because the aircraft is simply too heavy. We have asked for a cruise altitude greater than the maximum attainable at this weight. Let's now look at a serious alert message, insufficient fuel. We'll put ourselves into a typical situation first, then we'll work out how the FMS has arrived at this conclusion. Finally, we'll work out what we can do about it. Here is a route. We'll say that we don't normally take a more direct path because we have to follow the airways. There is an en route alternate. An alternate near the destination where the weather is bad. And an alternate further away where the weather is within limits when we take off. This is the one we have to nominate. You are here when you get the insufficient fuel message. Firstly, let's work out how the FMS has arrived at this conclusion. It knows where you are, and it is continuously working out the length of the rest of the route. It knows your ground speed, so it can work out the remaining flight time. It knows the present fuel and the fuel consumption rate, so it can work out how much you will have on arrival at the destination. It then compares this estimated fuel on arrival with the minimum reserves. Your first reaction might be to make an immediate en route diversion in order to stay within your fuel reserve minima. However, there may be other courses of action, and the FMS can help us perform these calculations and see whether the figures make these options viable. Firstly, you could ask air traffic control for a more direct routing. They might not be able to give it, but it's worth a try. If they say yes, the FMS can work out the new fuel used and revised fuel on arrival. This may solve your problem. You could also think about choosing a different flight level. Climbing 4,000 feet will probably give you a higher TAS and a better specific air range. If you have a strong headwind, perhaps going 4,000 feet lower might reduce it. In both cases, the FMS can work out the revised fuel and time for you. Also, it may be that since you took off, possibly several hours ago, the weather has changed en route. Maybe the nearer diversion is now within limits. If any of these solutions or a combination of the three works, then you can proceed safely and legally to your destination. The FMS is a very capable computer, but you don't follow its instructions blindly. It has various what-if options, which should be used sensibly. It does not replace the need for airmanship and captaincy. Let's summarize this lesson. The first 4 pages in the startup sequence are always the same: identification, position initialization, route and performance initialization. The route is usually entered simply using the operator's flight number. Cost index is determined by dividing aircraft operating costs by fuel costs. The range of values is then put on a sliding scale, which is from 0 to 200 for the Boeing Classic series of FMCs. 0 gives minimum trip fuel and 200 gives minimum flight time. A required time of arrival mode is available in order to arrive on time at some designated waypoint, such as the final approach fix, holding fix, or airport. New waypoints can be created by the pilots using one of the 4 acceptable entry methods. These cannot be entered into the permanent memory. The IRS position is not updated after initial entry. However, the FMS position is first updated on takeoff. Finally, we looked at some typical alert and advisory messages. This concludes the 2 lessons on the FMS.